66 million years ago, something the size of a small city hit the Earth at 43,000 miles per hour. It struck what is now the Yucatan Peninsula in Mexico, and in less than 10 seconds it released the energy of 10 billion nuclear weapons. The sky turned white. The ground liquefied. A wall of superheated rock and dust radiated outward at thousands of miles per hour, incinerating everything in its path for 1,000 miles in every direction. Within hours, fires raged across entire continents. Within days, the sky went dark. Within weeks, temperatures dropped by dozens of degrees. 75% of all species on the planet, including every non-avian dinosaur that had ruled the Earth for 165 million years, were erased, gone, not because they were weak, not because they failed to adapt, but because a rock, drifting silently through the emptiness of space, happened to cross the wrong orbit at the wrong time. That is what an asteroid can do. And the terrifying truth is this: it will happen again. Not might, will. The solar system is littered with millions of rocky objects, many of them hurtling through the inner solar system on paths that cross Earth's orbit. Some of them are a few feet wide, too small to worry about. Some of them are hundreds of feet wide, large enough to destroy a major city. And a small number of them are a mile across or larger, carrying enough energy to end civilization as we know it. The question has never been whether another catastrophic impact will happen. The question is when. And for almost the entire history of humanity, the answer to what we could do about it was nothing. We would see it coming, perhaps months in advance, perhaps years, and we would watch it fall. But on September 26, 2022, something extraordinary happened. A spacecraft no larger than a vending machine, traveling at roughly 14,000 miles per hour, slammed headfirst into an asteroid moonlet called Dimorphos. The collision was deliberate. It was planned years in advance. It was the culmination of decades of engineering, physics, and a single terrifying question that had haunted planetary scientists for generations. Can we actually move an asteroid? The mission was called DART, the Double Asteroid Redirection Test, and it was, by any measure, the most audacious thing humanity had ever attempted in space. Not because the spacecraft was large. It was not. Not because the technology was exotic. It was surprisingly simple. But because, for the first time in the 4.5 billion year history of our solar system, a species that evolved on one small rocky world reached out and deliberately changed the orbit of another celestial body. That had never happened before. Not once. Not anywhere in the known universe, as far as we can tell. And the result was not what anyone expected. The impact did not just nudge Dimorphos. It did not gently tap it off course by a few inches. It blasted over 20 million pounds of rocky debris into space, creating a tail of ejected material that stretched for thousands of miles. The orbit of Dimorphos around its parent asteroid, Didymos, shortened by 33 minutes. Scientists had hoped for perhaps 70 seconds. They got 33 minutes. That is more than 25 times the minimum expectation. The little moonlet was not just moved, it was shoved, hard, and the physics of why it moved so much more than predicted opened up a cascade of new questions about the nature of asteroids, the mechanics of impact, and the fragile, rubble-strewn bodies that drift through our neighborhood of space. This is a story about a rock, a very small rock, barely 530 feet across, roughly the size of a football stadium. It orbits another rock, called Didymos, which is itself less than half a mile wide. Together, they tumble through the inner solar system, bound by their own feeble gravity, two fragments of a universe that has been smashing things together for billions of years. Neither Dimorphos nor Didymos poses any threat to Earth. They were chosen, not because they are dangerous, but because they are the perfect test case. A binary system where the effect of an impact can be measured precisely from the ground. But the implications of what DART proved are staggering, because somewhere out there, right now, there are asteroids we have not yet found. Some of them are on orbits that will one day bring them close to Earth. Some of them are large enough to cause regional devastation, and a very small number of them, perhaps one or two that we have not yet catalogued, are large enough to threaten the survival of our species. DART was not just a science experiment. It was a rehearsal, a dress rehearsal for the day we might need to save the world. By the end of tonight, you are going to understand how a space rock the size of a stadium became the most important target in the history of planetary science. You are going to see how engineers built a spacecraft designed to destroy itself on purpose, how navigators guided it to a bullseye on a world so small it was barely a pixel in the best telescopes on Earth, and how the moment of impact revealed truths about asteroids that no one had anticipated. You are going to learn why Dimorphos might not be a solid rock at all, and why that changes everything about planetary defense. And you are going to confront a question that most people never think about, but that every scientist working on this problem carries with them every single day. What happens if the next one is too big, too fast, or too close for us to stop? Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. To understand why a spacecraft was deliberately crashed into a tiny moonlet orbiting an obscure asteroid, you first have to understand the neighborhood we live in. And that neighborhood is far more violent than it appears. On a clear night, the sky looks peaceful, stars hang motionless, the moon glows steadily. The planets trace their ancient paths with mathematical precision. It all seems stable, ordered, safe. But that picture is an illusion created by the shortness of human life. We live for 70 or 80 years on a planet that is 4.5 billion years old. In those few decades, we rarely see the violence that shapes the solar system. But it is always there, always has been. The craters on the moon are not decorations. They are scars, evidence of a bombardment so intense that every square inch of the lunar surface has been struck multiple times. The moon has no atmosphere, no weather, no tectonic activity. Its craters never heal. They are a permanent record of 4 billion years of cosmic collisions. And Earth, sitting right next to the moon, has been hit just as often. The difference is that Earth hides its wounds. Our atmosphere burns up the small impactors. Our oceans swallow the medium ones. Our tectonic plates recycle the crust, erasing ancient craters over millions of years. Rain, wind, and vegetation cover what remains. But the impacts happened. They are still happening. Every single day, roughly 100 tons of space debris enters Earth's atmosphere. Most of it is dust. Tiny particles that burn up harmlessly as meteors, the shooting stars that people wish upon. But mixed in with the dust are larger pieces. Pebbles, rocks, occasionally boulders. On February 15, 2013, the city of Chelyabinsk in Russia got a reminder of what those boulders can do. A rock roughly 60 feet across, about the size of a 6-story building, entered the atmosphere at a speed of over 40,000 miles per hour. It was so fast that the air in front of it could not move out of the way. It compressed, superheated, and the rock exploded at an altitude of roughly 18 miles, releasing the energy equivalent of 500,000 tons of TNT. That is roughly 30 times the energy of the atomic bomb dropped on Hiroshima. The shockwave shattered windows across the city. Over 1,500 people were injured, mostly by flying glass. Buildings shook. Car alarms screamed. Dashcam footage captured a second sun streaking across the morning sky, bright enough to cast sharp shadows at 9 in the morning. And here is the part that should keep you up at night. Nobody saw it coming. Not NASA, not the European Space Agency, not any of the ground-based surveys tasked with finding dangerous asteroids. The Chelyabinsk impactor approached Earth from the direction of the sun, completely invisible against the glare. There was no warning, no alert, no time to react. 1,500 people were hurt by an object that, by asteroid standards, was tiny, a pebble. If that rock had been 10 times larger, 600 feet, instead of 60, the explosion would have been powerful enough to flatten a major metropolitan area, and no one would have seen it coming either. This is the reality of planetary defense. The solar system is a shooting gallery, and Earth is one of the targets. Chelyabinsk was not even the most dramatic example. In 1908, something exploded over a remote region of Siberia near the Podkamennaya Tunguska River with a force estimated at 3 to 15 megatons of TNT, hundreds of times more powerful than the Chelyabinsk event. The blast flattened roughly 80 million trees across 800 square miles of forest. It knocked people off their feet dozens of miles away. The night sky across Europe glowed for days afterward, bright enough to read a newspaper at midnight in London. Scientists later determined that the explosion was caused by an object roughly 130 to 160 feet across, likely a stony asteroid or a fragment of a comet, that detonated in the atmosphere at an altitude of 3 to 6 miles. No crater was ever found because the object disintegrated entirely before reaching the ground. But the destruction was immense. If the Tunguska event had occurred over London, or Paris, or New York, the city would have been leveled entirely. Millions would have died. And in 1908, just as in 2013, there was no warning whatsoever. The Tunguska and Chelyabinsk events bracket the range of impacts that are both frequent enough to worry about and devastating enough to cause significant harm. They happen on timescales of decades to centuries, not millions of years. They strike randomly, and until very recently, humanity had no way to detect them in advance, and absolutely no way to prevent them. The history of our understanding of this threat is surprisingly recent. For most of human civilization, rocks falling from the sky were considered myths, superstitions, or divine punishment. In the late 18th century, the idea that stones could fall from space was ridiculed by the scientific establishment. When villagers in France reported a shower of stones in 1768, the French Academy of Sciences sent the young chemist Antoine Lavoisier to investigate. He concluded that the stones were ordinary rocks that had been struck by lightning. The idea that they came from space was, in his view, absurd. It was not until 1803, when another spectacular meteorite fall occurred at L'Aigle in Normandy, witnessed by hundreds of people and investigated by physicist Jean-Baptiste Biot, that the scientific community finally accepted that, yes, rocks do fall from the sky. But accepting that meteors exist is very different from understanding that they could kill you. The gap between these two realizations is measured in centuries. Even after scientists accepted that meteorites came from space, the idea that large impacts could shape Earth's geology, let alone threaten life, took much longer to sink in. In the early 1900s, a mining engineer named Daniel Barringer became convinced that a giant crater in the Arizona desert, nearly a mile across and 570 feet deep, was formed by a meteorite impact rather than a volcanic explosion. He spent 26 years and much of his personal fortune trying to find the buried meteorite, drilling into the crater floor in search of a massive iron mass he believed lay beneath the surface. He never found it because the impactor had been vaporized on impact. But Barringer was right about the origin. The crater that now bears his name, Meteor Crater, or Barringer Crater, was indeed formed roughly 50,000 years ago by a nickel-iron meteorite about 150 feet across, traveling at roughly 29,000 miles per hour. The energy of the impact was equivalent to roughly 10 megatons of TNT. The explosion would have devastated everything within a radius of several miles. Barringer Crater was a landmark in impact science, but its significance was not widely appreciated for decades. Most geologists continued to attribute circular formations on Earth to volcanic processes. The intellectual resistance to impact as a geological force was deep-seated. The Earth was supposed to be shaped by slow, gradual processes: erosion, sedimentation, tectonic uplift. The idea that a sudden, violent event from space could reshape the landscape in seconds ran counter to the uniformitarian philosophy that had dominated geology since the early 19th century. It took the work of Eugene Shoemaker, the same scientist who would later co-discover Comet Shoemaker-Levy 9, to definitively prove in the 1960s that Barringer Crater was an impact structure. Shoemaker found minerals at the crater that could only be formed under the extreme pressures generated by hypervelocity impacts, pressures far beyond anything volcanism could produce. His work opened the door to recognizing impact craters around the world and, eventually, to understanding that impacts were not just geological curiosities but agents of mass extinction. For most of the 19th and 20th centuries, asteroid impacts were considered geological curiosities, interesting to study, but not particularly relevant to human civilization. The craters on the Moon were thought by many geologists to be volcanic. The idea that a large impact could cause a mass extinction was not seriously proposed until 1980, when physicist Luis Alvarez and his geologist son Walter published a paper that would change everything. The Alvarez team had been studying a thin layer of clay found in geological formations all over the world, right at the boundary between the Cretaceous and Paleogene periods. The exact moment, 66 million years ago, when the dinosaurs vanished. This clay layer contained an unusually high concentration of iridium, an element that is rare on Earth's surface but abundant in asteroids. The Alvarezes proposed that the iridium came from a massive asteroid impact, one large enough to throw so much debris into the atmosphere that it blocked sunlight for months, triggering a global winter that wiped out 75% of all species. The reaction from the scientific community was fierce. Paleontologists were outraged. Geologists were skeptical. The idea that a single event, a single bad day, could undo hundreds of millions of years of evolution seemed too dramatic, too catastrophic, too Hollywood. The Alvarez hypothesis was called everything from bold to reckless to irresponsible. Critics pointed out that massive volcanic eruptions, specifically the Deccan Traps in India, were occurring at the same time and could have caused the extinction without any asteroid at all. The debate raged for a decade, and then in 1991, the smoking gun was found. Researchers identified a massive buried crater near the town of Chicxulub on the Yucatan Peninsula in Mexico. The crater was roughly 110 miles across. It was exactly the right age, 66 million years. It was exactly the right size to have been created by an asteroid 6 to 9 miles wide, and it was exactly where the geological and chemical evidence said it should be. The Chicxulub impact was real, and its consequences were almost beyond comprehension. The asteroid struck shallow ocean water at a speed of roughly 12 miles per second. The energy released was equivalent to roughly 10 billion Hiroshima bombs, or about 100 million megatons of TNT. To put that in perspective, the largest nuclear weapon ever detonated by humanity, the Soviet Tsar bomber, yielded 50 megatons. The Chicxulub impact was 2 million times more powerful. The impact excavated a hole in the Earth's crust more than 12 miles deep. It launched molten rock high into the upper atmosphere, where it rained back down across the globe as tiny glass beads, billions of incandescent droplets that heated the atmosphere to oven-like temperatures. Forests ignited across continents. Soot and dust blocked the sun. Photosynthesis stopped. The food chain collapsed from the bottom up. And the asteroid that did all of this, it was perhaps 6 miles wide. On the scale of the solar system, that is nothing. If the sun were the size of a front door, the Chicxulub impactor would be smaller than a grain of sand. A grain of sand destroyed 75% of life on Earth. That is the scale of the threat we are talking about. After Chicxulub confirmed, the conversation about asteroid impact odds changed permanently. It was no longer a question of geology or paleontology. It was a question of survival. And in the 1990s, a series of events drove that point home with startling urgency. In 1994, the world watched as comet Shoemaker-Levy 9 broke apart and slammed into Jupiter over the course of 6 days. The fragments struck the gas giant with such force that they left dark scars in Jupiter's atmosphere, each one larger than the entire Earth. If those fragments had hit our planet instead, civilization would have ended. The images from the Hubble Space Telescope were broadcast around the world, and for many people, including many politicians, it was the first time they truly understood that cosmic impacts were not just a thing of the distant past. They were an ongoing threat. They could happen to us. They could happen tomorrow. This realization catalyzed a new era in planetary defense. In 1998, NASA established the Near-Earth Object Observations Program, tasked with finding and tracking at least 90% of near-Earth asteroids larger than 1 kilometer, about 0.6 of a mile in diameter. The reasoning was straightforward. An asteroid of that size or larger could cause a global catastrophe. Smaller ones could devastate regions or countries. The first step in defending against impacts is knowing what is out there. The political context of this decision is worth understanding. Throughout the 1990s, a series of congressional hearings examined the asteroid threat with increasing seriousness. The catalyst was not only Shoemaker-Levy 9, but also a growing body of scientific evidence that near-Earth asteroids were more numerous than previously thought. In 1990, the United States House of Representatives directed NASA to conduct 2 workshops on the detection and interception of asteroids and comets that could collide with Earth. The resulting SpaceGuard survey report, published in 1992, recommended a systematic search for objects larger than 1 kilometer. It estimated there were roughly 1,000 to 2,000 such objects in near-Earth space. The risk was not theoretical, it was actuarial. The probability of a civilization-ending impact within any given century was low, but it was not zero. And unlike most natural disasters, an asteroid impact is preventable if you see it coming and have the technology to do something about it. The search began in earnest with surveys operating from observatories in Arizona, New Mexico, and Hawaii. The Catalina Sky Survey, based at the University of Arizona's Steward Observatory, became one of the most prolific asteroid hunters, using wide-field telescopes to scan huge swaths of sky each night. Pan-STARRS, the Panoramic Survey Telescope and Rapid Response System, located on the summit of Halakala in Maui, brought unprecedented sensitivity to the search, capable of detecting faint, distant objects that earlier surveys had missed. The Lincoln Near-Earth Asteroid Research Program, known as LINEAR, operated by MIT's Lincoln Laboratory at the White Sands Missile Range in New Mexico, contributed thousands of discoveries in its early years. These surveys transformed our picture of the near-Earth environment. By the mid-2000s, the number of known near-Earth objects had grown from a few hundred to several thousand. Today, that number exceeds 34,000. The vast majority of the large ones, those over 1 kilometer, have been found. More than 95% of them are now tracked, and none of them are on a collision course with Earth in the foreseeable future. That fact alone represents one of the most significant and least celebrated achievements in the history of science. For the first time, humanity can say, with reasonable confidence, that no known asteroid will cause a global catastrophe in the next century. The nightmare scenario of a surprise extinction-level impact has been, if not eliminated, dramatically reduced, and the next generation of surveys promises to push even further. The Vera C. Rubin Observatory, currently under construction in Chile, will begin its legacy survey of space and time in the coming years, scanning the entire visible sky every few nights with the camera so sensitive it can detect objects as faint as a candle viewed from halfway across the solar system. It is expected to multiply the number of known near-Earth objects several times over, potentially finding the majority of the city killers that current surveys have missed. But here is the problem. The large asteroids are not the only threat. Objects in the range of 100 to 300 feet across, like the Chelyabinsk impactor, or even larger, are far more numerous and far harder to find. There are estimated to be more than 25 million near-Earth objects in that size range, and we have found less than 5% of them. Any one of them could appear on a collision course with little warning. And while a 100-foot asteroid would not end civilization, it could destroy a city. A 300-foot asteroid could devastate an area the size of a small country. A 500-foot asteroid, roughly the size of Dimorphos, could release the energy of hundreds of megatons of TNT, enough to trigger tsunamis, firestorms, and regional climate effects. Finding them is only half the problem. The other half is doing something about them. And for decades, that second half had no answer at all. The earliest serious proposals for asteroid deflection came in the 1960s and 70s, and most of them involved nuclear weapons. The logic was simple and brutal. If a large asteroid is heading for Earth, hit it with the biggest bomb you have and hope for the best. But this approach has serious problems. A nuclear detonation might shatter a large asteroid into several smaller pieces, and instead of one devastating impact, you could get a shotgun blast of fragments hitting a wider area. Worse, nuclear detonation in space is governed by international treaties, and the political complications of launching nuclear weapons into orbit, even for planetary defense, are enormous. Other proposals were more elegant. You could park a massive spacecraft next to an asteroid and let the feeble gravitational attraction between them slowly tug the asteroid off course over many years, a concept called the gravity tractor. you could paint one side of the asteroid white, changing how it absorbs and re-emits sunlight, creating a tiny thrust from the pressure of photons, the Yarkovsky effect. You could attach an ion engine to the asteroid and push it directly. All of these ideas are theoretically sound. None of them had ever been tested, and all of them require one thing that might not exist in a real emergency: decades of advance warning. The most straightforward option, and the one that could work with the least warning time, is the kinetic impactor. Hit the asteroid with something heavy, moving very fast. Transfer momentum. Change its velocity by a tiny amount. If you do it early enough, even a change of a fraction of an inch per second can accumulate over years into a deflection of thousands of miles, enough to turn a direct hit into a clean miss. The mathematics behind this are worth pausing to appreciate. An asteroid heading for Earth at typical encounter speeds, anywhere from 25,000 to 160,000 miles per hour, crosses the distance of the Moon's orbit in just a few hours. But give that asteroid a sideways nudge years or decades before the encounter, and the deflection amplifies over time. A change of 1 centimeter per second, applied 10 years before impact, can shift the asteroid's position by roughly 10,000 kilometers at the time of Earth crossing. That is more than the diameter of our entire planet. The nudge is tiny, the effect is enormous, but only if it is applied early enough. This is why detection and early warning are not separate from deflection. They are prerequisites for it. The later you find the threat, the harder you have to push. The urgency of developing a real deflection capability was underscored by a scare that rattled the planetary defense community in 2004. In June of that year, astronomers discovered a near-Earth asteroid roughly 1,100 feet across, about 3 football fields end to end. They named it 99942 Apophis. Initial orbital calculations gave it a startling 2.7% chance of hitting Earth on Friday, April 13, 2029. A 2.7% probability does not sound high, but for an impact that could release the energy of more than 1 billion tons of TNT and devastate an area the size of a European country, it was terrifying. For several days, Apophis held the highest rating ever recorded on the Torino Impact Hazard Scale, a level 4, indicating a close encounter with a significant chance of a regional catastrophe. Further observations eventually ruled out the 2029 impact, and subsequent data also eliminated a smaller risk of impact in 2036. But the episode was a wake-up call. Apophis showed that a threatening asteroid could be discovered with only years of warning, not decades, not centuries. And in 2004, humanity had no tested capability to deflect such an object. None. The concept is elegant, but the engineering is diabolical. You are trying to hit a target that might be 500 feet across, orbiting the Sun at tens of thousands of miles per hour, from a distance of millions of miles, using a spacecraft that has to navigate autonomously because the time delay for radio signals makes remote control impossible. The margin for error is essentially zero. A miss by even a few dozen feet means failure, and nobody had ever tried it until DART. But before we get to DART itself, it is worth pausing to understand just how staggering the scale of the asteroid problem truly is. The solar system contains hundreds of millions of asteroids. Most of them live in the main asteroid belt, a broad region between the orbits of Mars and Jupiter, stretching from about 128 million miles to roughly 297 million miles from the Sun. If you could see the asteroid belt from above, you might imagine it as a dense, dangerous swarm, a minefield of tumbling rocks, the way Hollywood often depicts it. But the reality is astonishingly empty. The average distance between asteroids in the main belt is about 600,000 miles. If you were standing on one asteroid and looking around, you would not see another one with the naked eye. The belt is vast and sparse, a graveyard of worlds that never formed. But not all asteroids stay in the belt. Gravitational interactions with Jupiter, the solar system's great bully, with a mass more than 300 times that of Earth, can nudge asteroids out of stable orbits and send them careening into the inner solar system. Over billions of years, this process has scattered millions of rocky fragments onto orbits that cross those of Mars, Earth, Venus, and Mercury. These are the near-Earth objects, and they are the ones that keep planetary scientists awake at night. The taxonomy of near-Earth objects is itself a lesson in threat assessment. They are divided into groups based on their orbits. The Asteroid asteroids orbit entirely inside Earth's orbit, closer to the Sun, rarely coming close to our planet. The Aten asteroids have orbits mostly inside Earth's, but cross it at their farthest point. The Apollo asteroids have orbits mostly outside Earth's, but cross it at their nearest point. These are the most common and, statistically, the most dangerous group. And the Amur asteroids orbit entirely outside Earth's orbit, but come close enough to be perturbed into Earth-crossing paths in the future. Dimorphos and its parent Didymos belong to the Apollo group. Their orbit takes them from just inside Earth's orbit out to roughly 2.3 times Earth's distance from the Sun. Twice during each orbit, the Didymos system crosses Earth's orbital path. To put the sheer scale of the hazard in perspective, consider this thought experiment. If you could shrink the entire inner solar system down to the size of a basketball court, Earth would be a tiny ball bearing rolling along one of the court lines. The asteroids that cross Earth's orbit would be thousands of nearly invisible specks of dust scattered across the court, each one slowly drifting along its own curved path. Most of them would never come anywhere near the ball bearing. But over millions of years, playing this game of cosmic billiards, a collision is inevitable on the real basketball court of the inner solar system, with real asteroids and a real Earth. The math says that a Chelyabinsk-class impact, an object roughly 60 feet across, happens about once every 50 to 100 years. A Tunguska-class event, an object roughly 130 feet across, like the one that flattened 800 square miles of Siberian forest in 1908, happens once every few hundred to 1,000 years. A civilization-threatening impact from an object a mile across or larger happens roughly once every 500,000 years, and an extinction-level event like Chicxulub happens once every 100 million years or so. Those timescales sound comforting until you realize two things. First, the impacts are random. Once every 100 years does not mean the next one is 100 years away. It means there is roughly a 1% chance of one happening in any given year. That is a coin flip over a human lifetime. Second, even the small impacts, the city killers, the regional devastators, happen on timescales short enough to be relevant to civilization. Tunguska happened in 1908. Chelyabinsk happened in 2013. The next one could happen next year, next decade, or tomorrow. We simply do not know. It was this gnawing uncertainty that drove the development of the kinetic impactor concept. And it was the sheer difficulty of validating that concept that made the Didymos-Dimorphos binary system such an attractive target. The idea of a kinetic impactor test mission had been circulating in the planetary defense community since the late 1990s. The European Space Agency explored a concept called Don Quixote in the early 2000s, a two-spacecraft mission that would send one probe to observe an asteroid, while a second probe slammed into it. The concept was studied extensively, but ultimately shelved due to budget constraints. NASA's own internal studies examined multiple mission architectures before converging on the approach that would become DART, a single impact or spacecraft targeting the moonlet of a binary asteroid with the orbital change measured from the ground. The concept was formalized around 2011 and 2012, and DART was officially approved as a mission by NASA's Planetary Defense Coordination Office in 2015. The Double Asteroid Redirection Test began as a concept study at the Johns Hopkins University Applied Physics Laboratory, APL, in the early 2000s. The idea was deceptively simple: build a spacecraft, launch it toward a binary asteroid system, and crash it into the smaller of the two bodies at high speed. By targeting the moonlet in a binary system, scientists could measure the change in orbit from Earth, using the timing of mutual eclipses between the two asteroids as a natural clock. The target would be Dimorphos, the tiny moon of the near-Earth asteroid Didymos. But the simplicity of the concept masked extraordinary complexity. Dimorphos had never been seen as more than a faint fluctuation in the light of Didymos. Its size was estimated, not measured. Its shape was unknown. Its composition was unknown. Its surface properties were unknown. The spacecraft would be approaching a target it had never seen before, at a closing speed of roughly 4 miles per second, and it would have to find, track, and guide itself to impact in the final minutes of the approach, autonomously, with no human in the loop, navigating by the light of the target itself. And there was another problem, one that would not fully reveal itself until after the mission. Scientists assumed they knew, in rough terms, how the impact would go. They had models. They had simulations. They had laboratory experiments, firing tiny projectiles into sand and gravel. They expected DART's impact to create a small crater, eject some material, and change the orbital period of Dimorphos by roughly 70 seconds. Maybe more, maybe less, but somewhere in that range. They were wrong. Spectacularly, beautifully wrong. The answer was 33 minutes. And understanding why requires understanding something that nobody fully appreciated before the mission. Dimorphos might not be a rock at all. It might be something far stranger and far more fragile than anyone imagined. But that revelation would come later. First, the spacecraft had to be built, launched, and guided across 7 million miles of empty space to hit a bullseye the size of a football stadium. The problem with asteroids is not that they are mysterious. It is that they are deceptive. From a distance, through a telescope, an asteroid looks like a point of light, a tiny, cold, inert dot drifting through the blackness. It seems simple. It seems manageable. It seems like something you could push out of the way if you needed to. But the closer you look, the more complicated it gets. And the history of asteroid science is a history of assumptions being shattered, one after another, as each new mission and each new observation revealed a reality far stranger than anyone predicted. For most of the 20th century, asteroids were treated as afterthoughts, the leftovers of planetary formation, chunks of rock and metal that never managed to coalesce into a proper planet. The prevailing image was of solid, dense, potato-shaped boulders tumbling through space. When scientists talked about deflecting an asteroid, they imagined hitting a solid rock. The physics was straightforward. Mass times velocity equals momentum. Transfer enough momentum and the rock moves. Simple. But starting in the 1990s, a series of spacecraft encounters began to demolish that tidy picture. In 1991, the Galileo spacecraft, on its way to Jupiter, flew past the asteroid 951 Gaspra and returned the first close-up images of an asteroid ever taken. Gaspra was roughly 11 miles long, irregular and covered in craters, but it looked more or less like a solid rock. 2 years later, Galileo flew past another asteroid, 243 Ida, and discovered something astonishing. Ida had a tiny moon. It was the first asteroid moon ever found, a rock barely a mile across, orbiting its parent in a slow, delicate waltz. They named it Dactyl. The discovery proved that asteroids could have companions, that the gravitational environment around these small bodies was more complex than the simple picture of lonely rocks drifting through the void. Then came Near Shoemaker, the near-Earth asteroid rendezvous mission, which arrived at the asteroid 433 Eros in February of 2000. Eros is a large near-Earth asteroid, about 21 miles long, shaped like a peanut. Near Shoemaker orbited Eros for a year, mapping its surface in extraordinary detail. What it found was puzzling. Eros was covered in a fine layer of dust and gravel, called regolith, similar to what covers the Moon. Its surface was dotted with boulders, some as large as houses, and its interior density suggested that it was not entirely solid. There were voids inside, spaces where the rock did not quite fit together. Eros was cracked, fractured, held together more by habit than by strength, and it gets worse. In 2003, the Japanese space agency JAXA launched a mission called Hayabusa to the tiny asteroid 25143 Itokawa. When Hayabusa arrived in 2005, the images it sent back were unlike anything scientists had seen. Itokawa did not look like a rock. It looked like a pile of gravel. Its surface was a chaotic jumble of boulders, pebbles, and dust, with no visible craters at all. The absence of craters was a critical clue. It meant the surface was not solid enough to preserve them. Impacts did not leave marks because the surface simply rearranged itself, like poking a finger into a jar of loose sand. Itokawa was not a rock. It was a rubble pile, a loose aggregate of fragments held together by nothing more than their own feeble gravity. If you could somehow pick it up, it might crumble in your hands. This was a revelation, and it changed the entire framework for thinking about asteroid deflection. But the surprises were not over. In 2016, NASA launched OSIRIS-REx, the origins, spectral interpretation, resource identification, and security regolith explorer, to the near-Earth asteroid 101955 Bennu. Bennu is a small body, about 1,610 feet across, classified as a potentially hazardous asteroid, with a very small but non-zero probability of impacting Earth in the late 2200s. When OSIRIS-REx arrived at Bennu in December of 2018, the science team expected to find a relatively smooth surface, sandy and fine-grained, easy to sample. What they found instead was a boulder-strewn nightmare. The surface of Bennu was covered in rocks, many of them the size of cars and houses, with very little smooth terrain in between. The landscape was so rugged that the team had to completely redesign their sample collection approach, targeting a site barely the size of a few parking spaces among the boulders. But even more striking was what OSIRIS-REx revealed about Bennu's internal structure. The asteroid's bulk density, the total mass divided by total volume, was only about 1.19 grams per cubic centimeter. For comparison, ordinary rock has a density of about 2.5 to 3 grams per cubic centimeter. Bennu's low density meant that roughly 40% of its interior volume was empty space, voids, gaps, and cavities between loosely stacked fragments. Bennu was not a solid body. It was, like Itokawa, a rubble pile. But it was a large rubble pile, and the detailed measurements from orbit confirmed that its structure was astonishingly fragile. In fact, during the sample collection attempt in October of 2020, when OSIRIS-REx's sampling arm touched the surface and fired a puff of nitrogen gas to stir up material, the arm sank nearly half a meter into the surface before the spacecraft's thrusters pulled it back. The surface of Bennu had the consistency of a ball pit. If the spacecraft had not fired its thrusters to back away, it might have been swallowed entirely. This was the context in which DART was heading toward Dimorphos. Mission after mission, asteroid after asteroid, the evidence was converging on a single uncomfortable truth. Many of the small bodies in our solar system are not the hard, solid rocks that planetary defense models were originally built to handle. They are fragile aggregates, held together by whispers of gravity, their interiors riddled with voids, their surfaces barely cohesive enough to maintain a shape. Hitting one of these objects with a kinetic impactor is not like hitting a billiard ball. It is like hitting a cloud of gravel that happens to be traveling in formation. Because if a significant fraction of asteroids are rubble piles rather than solid rocks, then hitting them with a kinetic impactor is a completely different problem. When you hit a solid rock, the energy goes into the rock. It cracks, it moves, it behaves predictably. When you hit a rubble pile, the energy dissipates through millions of loosely connected fragments. The surface absorbs the blow. The structure deforms. The ejector, the material blasted out by the impact, behaves differently because it is not being excavated from solid stone. It is being launched from what is essentially a gravel pile in space. This matters enormously for planetary defense. The amount of momentum transferred to an asteroid by a kinetic impactor depends not just on the mass and speed of the impactor, but on how much material the impact blows off the asteroid. Every kilogram of ejector that flies away from the impact site gives the asteroid an additional push in the opposite direction, thanks to Newton's third law. For every action, there is an equal and opposite reaction. If the impactor hits and barely ejects any material, the push is small, just the momentum of the spacecraft itself. If the impactor hits and blasts a massive plume of debris into space, the push can be many times larger, because all that departing mass is effectively a rocket exhaust, shoving the asteroid in the opposite direction. The ratio between the total momentum change and the momentum of the impactor alone is called the beta factor. If beta equals 1, the impact transferred only the spacecraft's own momentum, no boost from ejector. If beta equals 2, the ejector doubled the effect. If beta equals 5, the ejector contributed 4 times more momentum than the spacecraft itself. Before DART, the models predicted a beta of somewhere between 1.5 and 3 for a typical rubble pile asteroid. But the models were built on assumptions. Laboratory experiments at tiny scales, computer simulations with idealized conditions, and educated guesses about what the surface of Dimorphos actually looked like. Nobody had ever hit a real asteroid at full speed and measured the result. This is why Dimorphos was chosen. Not because it was dangerous, it was not. Not because it was particularly interesting in itself. Before DART, it was one of thousands of unremarkable small bodies in near-Earth space. Dimorphos was chosen because it orbits another asteroid. This is the key. If DART had targeted a solitary asteroid, measuring the change in orbit would have required incredibly precise tracking over months or years. But because Dimorphos orbits Didymos, completing one orbit roughly every 11 hours and 55 minutes, any change in that orbital period would show up almost immediately in the light curve. The pattern of brightness changes as Dimorphos passes in front of and behind Didymos as seen from Earth. It was a natural experiment with a built-in clock. The Didymos system was discovered in 1996 by the Spacewatch survey at the University of Arizona. Didymos itself is roughly half a mile across, about 780 meters, a fast-spinning, oblate body that rotates once every 2.26 hours. That rotation rate is significant. It is very close to the spin limit for a rubble pile body, the speed at which centrifugal force at the equator equals gravitational attraction, and loose material starts to fly off. Many scientists believe that Dimorphos was born from Didymos, that the parent body spun up over millions of years, driven by the gentle torque of sunlight, until material at its equator was flung off and gradually coalesced into a small moonlet. If this is true, then Dimorphos is not a captured rock. It is a child of Didymos, assembled from the debris shed by its own parent. And that means Dimorphos would inherit Didymos's rubble pile nature, loosely bound, weakly cohesive, held together by gravity so faint that a human standing on its surface would weigh about as much as a few sheets of paper. Imagine that. A world where gravity is so weak that if you jumped, you would not come back down for hours. A world where throwing a baseball would send it into orbit. A world where the surface is a jumble of boulders and gravel, with gaps and voids between them, and the whole structure could be disrupted by a force that, on Earth, would barely rattle a coffee cup. That is Dimorphos. But here is the problem, and it is a problem that haunted the DART team for years before launch. If Dimorphos is that fragile, what happens when you hit it with a half-ton spacecraft at 14,000 miles per hour? Does it absorb the blow like a sandbag? Does it shatter into a cloud of debris? Does the ejector enhance the deflection? Or does the loose structure dissipate the energy in ways that reduce it? The models disagreed. Different assumptions about the internal structure, how tightly the rubble was packed, how much cohesion existed between fragments, how deep the regolith layer was, produced wildly different predictions for the beta factor, the orbital period change, and the overall success of the deflection. And this uncertainty pointed to a deeper, more unsettling problem for planetary defense. We can find asteroids, we can track their orbits with extraordinary precision. We can predict, decades in advance, whether a given asteroid will come close to Earth. But when it comes to actually deflecting one, we are guessing. We are building our entire planetary defense strategy on models that have never been validated against a real impact on a real asteroid. DART was supposed to change that. It was supposed to turn guesswork into data. But even the act of testing raised uncomfortable questions. What if the test revealed that our models were dangerously wrong? What if the answer showed that kinetic impact, the simplest and most practical deflection method, only works under specific conditions that many real asteroids do not meet? The engineering challenge of actually reaching Dimorphos was almost as daunting as the scientific uncertainty about what would happen when DART arrived. The spacecraft itself was a marvel of focused engineering. Built by the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland, DART was deliberately designed to be simple, relatively inexpensive, and expendable. The spacecraft's body was a box roughly the size of a large refrigerator, about 3.9 feet on each side. It weighed roughly 1,210 pounds at launch, including fuel. For power, DART carried two enormous rollout solar arrays, the ROSA arrays, or rollout solar arrays, each one about 28 feet long. When deployed, the spacecraft's total wingspan stretched about 59 feet, wider than a school bus is long. These arrays were a new technology being tested for the first time in deep space, and they worked flawlessly throughout the mission, generating the power needed for DART's instruments and its electric propulsion system. DART carried a single scientific instrument, the Draco camera, but it also carried a technology demonstration that could reshape future missions. The spacecraft was equipped with the Next-C ion thruster, an advanced solar electric propulsion engine that uses charged xenon atoms for thrust. Ion engines produce extremely low thrust, barely enough to lift a sheet of paper on Earth, but they are extraordinarily efficient, and they can run for months or years, gradually building up enormous velocities. DART used the Next-C thruster to demonstrate the technology in deep space, running it for extended periods during the cruise phase to test its performance for future missions. DART launched on November 24, 2021, from Vandenberg Space Force Base in California, atop a SpaceX Falcon 9 rocket. The launch was routine. The journey was anything but. For 10 months, DART cruised through the inner solar system, its solar arrays drinking in sunlight, its navigation systems periodically checking its course against the stars. The mission operations team at APL monitored every parameter, tweaking the trajectory with small course corrections called trajectory correction maneuvers. These were gentle nudges, fractions of a mile per hour, that accumulated over months to ensure the spacecraft would arrive at precisely the right place at precisely the right time. The final approach began on September 26, 2022. The spacecraft had to travel roughly 7 million miles from Earth to reach the Didymos system, closing in on its target at roughly 4 miles per second, about 14,400 miles per hour. At that speed, the spacecraft crossed the distance between New York and Los Angeles in about 10 minutes, and it had to hit a target 530 feet across. From 7 million miles away, that target subtended an angle smaller than what the human eye can perceive. It was like standing in New York and trying to thread a needle held by someone in San Francisco, while both of you are moving at different speeds in different directions. Traditional spacecraft navigation relies on ground control. Engineers on Earth track the spacecraft using radio signals, calculate course corrections, and upload commands. But at DART's approach speed, the time delay for radio signals, even at the relatively close distance of 7 million miles, made real-time control impossible. A signal traveling at the speed of light takes about 38 seconds to travel from Earth to the spacecraft and back. In 38 seconds, DART would cover more than 150 miles. By the time engineers on the ground saw what was happening and sent a correction, it would be far too late. So DART had to guide itself. The spacecraft carried an instrument called Draco, the Didymos reconnaissance and asteroid camera for optical navigation, which was essentially a high-resolution camera coupled to an autonomous navigation algorithm called SmartNav, the small body maneuvering autonomous real-time navigation system. In the final 4 hours of the approach, SmartNav took over. It identified Didymos as a point of light against the star field, locked onto it, and began steering DART toward it. As the spacecraft closed in, Dimorphos gradually became visible, separating from the glare of Didymos as a faint secondary point of light. In the final 90 minutes, SmartNav switched its lock from Didymos to Dimorphos and began guiding the spacecraft to its final destination. The images that DART sent back during those last minutes are haunting. At first there is nothing, just a dark sky with a bright dot. Then the dot resolves into two objects, Didymos, larger, and Dimorphos, smaller, hugging close to its parent. As the minutes tick down, Dimorphos grows. Details emerge. The surface comes into focus. Boulders appear. Shadows sharpen. In the final seconds, the camera fills with rock, a landscape of grey boulders and gravel, starkly lit, completely alien. The last image, taken just 1 second before impact, shows a patch of surface roughly 100 feet across, strewn with rocks of all sizes. And then the feed cuts to black. Contact was lost at 7:14 p.m. Eastern Time on September 26, 2022. DART was destroyed on impact, as planned. In the Mission Operations Center at the Applied Physics Laboratory in Laurel, Maryland, the room erupted. Engineers and scientists who had spent years building this moment, designing the spacecraft, writing the navigation algorithms, planning the observations, leaped to their feet. Some cheered, some cried. Some simply stared at the screen where, moments before, a cascade of images had shown the surface of an alien world rushing closer and closer, and then nothing. A blank screen. The signal was gone, and that meant the mission had succeeded. DART had found its target, crossed millions of miles of empty space, and struck Dimorphos within 55 feet dead center. The autonomous navigation system had performed flawlessly. The spacecraft hit almost exactly where the scientists had aimed it, on the surface between two large boulders, in a region that would maximize the ejector plume. The collision transferred DART's full momentum, and whatever additional momentum the ejector provided, to Dimorphos. The impact occurred at a speed of roughly 6.1 kilometers per second, or about 13,650 miles per hour. The spacecraft's mass at impact was roughly 570 kilograms, about 1,258 pounds. The energy released was equivalent to roughly 3 tons of TNT, enough to demolish a building, but laughably small compared to the energies involved in natural asteroid impacts. To put this in perspective, the Chicxulub impact that killed the dinosaurs released roughly 10 billion times more energy. DART's impact was, by cosmic standards, the gentlest of taps, a mosquito landing on a freight train. And yet, that modest collision changed the orbit of a world. But DART did not die alone. 15 days before the impact, the spacecraft had released a tiny companion, Lycia Cube, the light Italian CubeSat for imaging of asteroids, built by the Italian Space Agency. Lycia Cube was about the size of a loaf of bread, equipped with 2 cameras, and its sole job was to fly past Dimorphos 3 minutes after DART's impact and photograph the aftermath. It was the witness to the crime, and the images it returned were extraordinary. They showed a massive cone of debris erupting from the impact site, expanding outward in a brilliant spray of dust and fragments, backlit by the sun. The ejector cloud was far larger and more dramatic than many scientists had expected. Lycia Cube captured something that no telescope on Earth could see. The first moments after humanity's first attempt to alter the course of a celestial body, frozen in images taken from just 55 kilometers away. Meanwhile, back on Earth, a global observation campaign was already underway. More than 30 telescopes on 5 continents had been coordinated to observe the Didymos system before, during, and after the impact. The Southern Hemisphere observatories were particularly important. The impact occurred when Didymos was best visible from South Africa, Chile, and other southern locations. Telescopes ranging from small amateur instruments to the 8-meter, very large telescope in Chile's Atacama Desert trained their optics on a faint dot of light and watched for changes. The first confirmation came quickly. Within hours, the light curve of the Didymos system, the regular pattern of brightness changes as Dimorphos orbited, showed a clear shift. The dip in brightness that occurred when Dimorphos passed behind Didymos was happening earlier than expected. The orbit had changed. Over the following days and weeks, repeated measurements refined the number. The orbital period of Dimorphos had decreased from 11 hours and 55 minutes to 11 hours and 23 minutes, a change of 32 minutes, later refined to 33 minutes. The numbers are striking. The prediction had been a change of perhaps 73 seconds at minimum. The actual change was more than 25 times that. But here is what makes this truly terrifying. The result revealed a Dimorphos that nobody had fully imagined before the mission. The orbital period change of 33 minutes was so far beyond the predictions that it forced scientists to fundamentally reconsider what Dimorphos actually is. The most likely explanation, supported by the massive ejector plume observed by telescopes on Earth and in space, is that Dimorphos is so loosely packed, so weakly held together, that the impact sent an enormous fraction of its surface material flying into space. The ejector did not just enhance the deflection, it dominated it. The momentum contributed by the departing debris was several times larger than the momentum of DART itself. Estimates of the beta factor ranged from 2.2 to 4.9, depending on the model and the assumptions. That means the rubble that flew off Dimorphos pushed it harder than the spacecraft did. And this raises a question that goes far beyond one mission and one moonlet. If Dimorphos, a body we chose specifically as a test case, turned out to be this different from our models, What about the asteroids we might actually need to deflect someday? How wrong are our assumptions about them? If a real threat were identified, and we launched a kinetic impactor based on our best models, would the result be twice as effective as expected? Half as effective? Would the asteroid fragment instead of deflecting? Would the impact trigger a cascade of structural failure in a rubble pile, turning one dangerous object into a cloud of still dangerous fragments? Something is wrong with our assumptions. Not catastrophically wrong. DART proved that kinetic impact works. That is a triumph. But the degree to which the result deviated from predictions is a warning. It tells us that our understanding of asteroid interiors, their density, their cohesion, their response to high-speed impacts, is still dangerously incomplete. And in a real emergency, incomplete understanding could mean the difference between deflecting a threat and making it worse. There is another dimension to this problem that rarely makes headlines but matters enormously. The shape of Dimorphos before DART arrived told a story that scientists are still trying to read. When the Draco camera resolved Dimorphos for the first time, it revealed a shape that surprised many researchers. Dimorphos was not the irregular potato-like lump that many asteroids resemble. It was roughly oblate, somewhat flattened, like a lens or a thick M&M candy. Its equatorial diameter was about 170 meters, while its polar dimension was closer to 116 meters. That shape is not random. It is a signature of how Dimorphos formed, and how material settled under its weak gravity. If Dimorphos coalesced from debris shed by a spinning Didymos, the material would naturally settle into an oblate shape, with more mass concentrated at the equator. This is consistent with the rubble pile formation model, and it means Dimorphos's internal structure is likely not uniform. The density might vary from region to region. Voids of different sizes might be scattered throughout the interior. Some areas might be loosely packed gravel, while others might contain larger, more cohesive chunks. This internal heterogeneity is a nightmare for impact modeling. When DART struck Dimorphos, the specific outcome depended not just on the speed and mass of the impactor, but on the exact properties of the material at the point of impact. Did the spacecraft hit a region of loosely packed pebbles or a larger, more solid boulder? Was there a void just beneath the surface that allowed the shockwave to propagate differently? Were the fragments near the impact site bonded by weak van der Waals forces, the feeble electrostatic attraction between dust grains, or were they simply resting against each other with no cohesion at all? These are not academic questions. They determine whether a kinetic impactor is a precision instrument or a blunt tool, and the answers depend on knowing things about asteroid interiors that we currently cannot measure from Earth. You are not X-ray an asteroid from a distance of millions of miles. You cannot drill into one without sending a spacecraft to its surface. You cannot even determine its density with high confidence unless you can measure both its mass and its volume independently. And for small bodies like Dimorphos, those measurements are extraordinarily difficult. The DART impact also revealed something unexpected about the dynamics of the Didymos-Dimorphos system. Before the impact, Dimorphos orbited Didymos at a distance of roughly 1.18 kilometers, about 3/4 of a mile. After the impact, the orbit was not only shorter in period, but also changed in eccentricity. The orbit became slightly more elliptical, meaning that Dimorphos's distance from Didymos now varies more over each orbit than it did before. This is a subtlety that carries large implications. A circular orbit is dynamically simple. An eccentric orbit introduces tidal effects. The gravitational pull of Didymos stretches and squeezes Dimorphos slightly differently at different points in its orbit, which can dissipate energy as heat and gradually reshape the moonlet over time. The impact, in other words, did not just change where Dimorphos goes, it may have changed what Dimorphos becomes. There is a scenario that some researchers have quietly discussed, one that edges into the territory of genuine concern for future deflection missions. What if a kinetic impact on a loosely bound rubble pile does not just eject surface material, but fundamentally destabilizes the body's internal structure? What if the shockwave propagating through a rubble pile creates a cascade of settling, shifting, and collapse that changes the asteroid's shape, its spin rate, or its structural integrity? In the worst case, a sufficiently energetic impact on a sufficiently fragile body might cause partial or total disruption, breaking the asteroid into multiple large fragments, each one still on a collision course with Earth, but now impossible to track individually. Instead of one 600-foot threat, you would face a swarm of 100-foot fragments, spread across a wider area, impossible to deflect individually, and collectively just as dangerous. This nightmare scenario is unlikely, and the DART results suggest that Dimorphos did not come close to disruption. But unlikely is not impossible, and the gap between the predicted and observed results is a stark reminder that our models are not yet reliable enough to rule out worst-case outcomes with confidence. Planetary defense cannot afford to be approximately right. It needs to be precisely right, because the stakes are existential. There is also the question of what happened to Dimorphos' shape after the impact. Before DART, the moonlet was roughly oblate, wider than it was tall, but the 33-minute change in orbital period implies a significant transfer of momentum, and some models suggest that the impact could have reshaped Dimorphos entirely. If enough material was blasted away from one side, the moonlet's center of mass would shift, its rotation could change, its shape could deform under the asymmetric loss of material. In the most extreme models, the impact may have transformed Dimorphos from an oblate spheroid into something more elongated, or created a large impact basin that fundamentally altered the body's surface geometry. Without close-up images of the post-impact Dimorphos, scientists could only guess. They needed to see the crime scene up close. They needed Hera. The fundamental lesson of the DART investigation is one that runs through all of science, but is especially acute in planetary defense. You cannot defend against what you do not understand. And our understanding of asteroids, their composition, their cohesion, their internal architecture, their response to external forces, is still in its infancy. We have visited fewer than a dozen asteroids with spacecraft. We have sampled only 2. We have impacted only 1. The universe of small bodies is vast and diverse, and each new encounter has shown us that our assumptions were incomplete, often in ways that matter profoundly for defense. The history of asteroid exploration reads like a chronicle of humility. Every time scientists thought they understood these objects, a new mission arrived and proved them wrong. Gaspra was not what they expected. Eros was not what they expected. Itakoa was not what they expected. Bennu was not what they expected. And Dimorphos, the one they actually hit, responded in a way that confounded the models by a factor of 25. If there is a pattern here, it is that asteroids are reliably surprising. They are not simple, they are not uniform, they are not easily categorized or predicted, and the one we need to deflect someday will, in all probability, be different from every one we have studied before. The DART mission did not just answer a question, it opened a door onto a landscape of new questions, each one more urgent than the last. And to understand those questions, and what they mean for the future of planetary defense, we need to look deeper, at the rubble, at the physics, at the fragile, crumbling worlds that drift unseen through our cosmic neighborhood, carrying the potential for both destruction and revelation. The mission planners knew from the beginning that DART would raise more questions than it answered. That was, in a sense, the point. Science does not progress by confirming what we already know. It progresses by revealing what we do not. And Dimorphos, in the brief moment of its encounter with a human-built machine, revealed more about the nature of small bodies in our solar system than decades of telescopic observation had managed. Consider the ejector itself. In the hours and days following the impact, telescopes around the world, and the Hubble Space Telescope and the James Webb Space Telescope in orbit, tracked the plume of debris streaming away from Dimorphos. The plume was enormous. It stretched for thousands of miles, forming a comet-like tail that was visible for weeks. The amount of material ejected was estimated at somewhere between 2 million and 20 million pounds, far more than the mass of the DART spacecraft itself. This material did not just float away gently. It was blasted out at speeds ranging from a few feet per second to several hundred feet per second, forming complex patterns of streaming debris that evolved over time as solar radiation pressure, the gentle push of sunlight, shaped the tail. The Hubble observations were particularly revealing. In the days after impact, Hubble captured images showing the ejector evolving from a roughly conical spray into a complex, structured tail. Then, surprisingly, the tail began to split. Roughly 17 days after the impact, Hubble detected a second tail emerging from the debris, a feature that astronomers compared to the twin tails sometimes seen in comets. The double tail suggested that the ejector dynamics were far more complex than a simple explosion. Material was being swept away from Dimorphos by solar radiation pressure at different rates depending on particle size, and the interaction between the ejector cloud and the Didymos system's gravity was creating patterns that no one had predicted. The debris was not just flying away in a straight line. It was swirling, clumping, and interacting with itself in a gravitational environment so weak that even the pressure of sunlight was a dominant force. The James Webb Space Telescope, freshly operational and the most powerful infrared observatory ever built, observed the system at wavelengths invisible to the human eye. Webb detected thermal emission from the ejector, the heat signature of dust and fragments warmed by the sun. These observations helped scientists estimate the size distribution of the ejected particles, which ranged from fine dust to chunks several inches across. The diversity of particle sizes confirmed that the impact had excavated material from multiple layers of Dimorphos' surface, disrupting a structure that was heterogeneous from top to bottom. The complexity of the ejector told scientists something profound about the surface of Dimorphos. This was not a crater being punched into solid rock. This was a loose structure being violently disrupted. The energy of the impact propagated through the rubble pile in ways that solid body models simply cannot replicate. Shock waves moved differently. Fragments interacted. Voids collapsed. The surface responded not as a unified solid, but as a collection of individual particles, each one responding to the forces acting on it. In some ways, the impact on Dimorphos had more in common with hitting a sandcastle than with hitting a boulder. And this is where the science becomes not just interesting, but critical for the future of our species. Because if a significant fraction of potentially hazardous asteroids are rubble piles, and current evidence suggests that many of them are, then our ability to deflect them depends on understanding exactly how rubble piles respond to impacts. Get the physics right, and we can calibrate our impactors to deliver precisely the right amount of deflection. Get the physics wrong, and we might overshoot, undershoot, or, worst of all, break the target apart in ways that increase the danger instead of reducing it. DART gave us the first real data point. One impact, one asteroid, one measurement. It is a beginning, not an ending, and the scientists who analyzed the results were the first to say so. As Andy Rivkin, the DART investigation team lead at the Applied Physics Laboratory, put it, the result was a great deal more effective than the minimum we were expecting, and it raised a whole new set of questions we need to answer. Those questions are specific and urgent. What does the impact crater look like? How deep is it? Did the impact penetrate to a denser layer beneath the surface, or did it excavate only the loose upper regolith? How did the shape of Dimorphos change? Did the impact alter the moonlet's spin? Did any material fall back onto the surface after being ejected? And if so, did it change the surface properties? What is the precise mass of Dimorphos? A number that is essential for calculating the exact momentum transfer and beta factor. These are not questions that can be answered from Earth. They require a spacecraft in orbit around Dimorphos, carrying instruments that can map the surface, probe the interior, and measure the gravitational field with exquisite precision. Those questions would require a new mission, a new spacecraft, and a close-up investigation of the crime scene. That mission already had a name, Hera, and it was already being built. The story of planetary defense did not end when DART's signal went dark. In many ways, it had only just begun. The impact on Dimorphos was a single data point, a proof of concept that raised more questions than it answered. And in the years that followed, a series of missions, proposals, and discoveries began to fill in the picture, each one a chapter in humanity's slow, painstaking effort to build a shield against the sky. The first and most important of these chapters belongs to Hera. Hera is a European Space Agency mission, named after the Greek goddess of marriage, a fitting name for a spacecraft whose purpose is to study a relationship, specifically the relationship between Didymos and Dimorphos after DART's violent intervention. Hera launched on October 7, 2024, aboard a SpaceX Falcon 9 rocket from Cape Canaveral, Florida. It is currently on its way to the Didymos system, where it is expected to arrive in late 2026. And when it gets there, it will become the most thorough investigation of an asteroid system ever conducted. The journey to approval was not easy. Hera's predecessor was a more ambitious concept called the Asteroid Impact Mission, or AIM, which ESA proposed in the early 2010s as a companion to DART. AIM would have arrived at Didymos before DART, establishing a presence at the asteroid system and observing the impact in real time from orbit. It was a beautiful concept, a complete end-to-end planetary defense experiment, with before and after observations from close range. But in December of 2016, ESA's Ministerial Council declined to fund AIM. The budget was too high. Other priorities took precedence. The decision stunned the planetary defense community. Without AIM, DART would fly alone, and the critical before and after comparison would be lost. The disappointment was acute, but it did not last. A smaller, more focused version of AIM was redesigned and rebranded as Hera. It would arrive after DART rather than before, studying the aftermath rather than witnessing the impact. The redesigned mission won approval at ESA's ministerial meeting in November of 2019, and construction began at OHB in Germany. The cost was roughly €363 million, a substantial investment, but one that ESA's member states agreed was justified by the stakes involved. Hera carries a suite of instruments designed to answer the questions that DART left open. Its primary camera, called the Asteroid Framing Camera, will map the surface of both Didymos and Dimorphos in high resolution, revealing the impact crater, or whatever remains of it, in sharp detail. A thermal infrared imager will measure surface temperatures, helping scientists understand the physical properties of the regolith, and a laser altimeter will map the topography of both bodies with centimeter-level precision, building three-dimensional models of shapes. But Hera's most innovative feature is its passengers. The spacecraft carries two CubeSats, tiny, shoebox-sized satellites called Milani and Juventas, that will be deployed near Dimorphos to conduct close-up investigations that the main spacecraft cannot perform safely. Juventas carries a low-frequency radar that will attempt to see inside Dimorphos, mapping its internal structure for the first time. If the moonlet is indeed a rubble pile, a loose collection of fragments with voids and gaps between them, the radar should reveal that structure directly, replacing decades of inference with direct measurement. Milani carries a hyperspectral camera and a dust detector, designed to study the composition of the surface and any residual dust environment left over from the DART impact. The importance of Hera's radar cannot be overstated. Before Hera, everything scientists knew about Dimorphos' interior was inferred, calculated from density estimates, modeled from impact simulations, guessed from the behavior of the ejector plume. Hera's radar will provide the first direct look inside an asteroid that has been deliberately impacted by a spacecraft. It will reveal the distribution of voids, the sizes of internal fragments, the degree of compaction, and potentially even the presence of ice or other volatile materials that could change the picture entirely. If the radar shows that Dimorphos is loosely packed throughout its volume, a bag of gravel with minimal cohesion, that has one set of implications for future deflection strategies. If it shows that Dimorphos has a more complex interior, perhaps a denser core surrounded by a loose mantle, or large monolithic fragments embedded in a matrix of rubble, that has very different implications. The beta factor, the key parameter for kinetic impactor effectiveness, depends critically on these internal properties. Without knowing them, every deflection calculation carries large uncertainties. With Hera's data, those uncertainties can be dramatically reduced. Hera will also measure the mass of Dimorphos directly, using the gravitational pull that the moonlet exerts on the spacecraft and the CubeSats during close approaches. This measurement is essential. The beta factor, the ratio of total momentum change to the impactor's momentum, can only be calculated precisely if the mass of the target is known. Before DART, Dimorphos's mass was estimated from its size and assumed density, with uncertainties of roughly 30 to 50%. Those uncertainties propagate directly into the beta calculation, making it difficult to know whether the ejector contributed twice the spacecraft's momentum, or 4 times, or somewhere in between. Hera's mass measurement will collapse those uncertainties and give planetary defense scientists a precise calibration point for future missions. There is another dimension to Hera's investigation that is less discussed but potentially revolutionary. Hera will study the Didymos-Dimorphos system as a dynamical laboratory, a natural experiment in binary asteroid physics. How does Dimorphos's orbit evolve over time after the DART impact? Is it stable or is it drifting? Are there tidal effects between the two bodies that are slowly reshaping the orbit? Is Dimorphos tidally locked to Didymos, always showing the same face, like the Moon does to Earth? Or has the impact knocked it out of that state? These dynamical questions matter because they inform how a deflected asteroid behaves after the intervention. If a kinetic impactor changes an asteroid's orbit, the new orbit needs to remain safe. If tidal effects or other dynamical processes cause the orbit to evolve in unexpected ways after deflection, that could complicate the mission's success. Hera, then, is not just a follow-up to DART. It is the second half of a complete planetary defense experiment, the part where the doctors examine the patient after the surgery to understand exactly what happened and why. Without Hera, the DART mission's legacy would be a single number, 33 minutes, with no way to fully explain it. With Hera, that number becomes a rich dataset, a calibration standard, and a foundation for every future deflection mission. But Hera addresses only the how of deflection, how asteroids respond to impacts, how their interiors are structured, how the ejector contributes to momentum transfer. The equally urgent question is the what. What asteroids are out there that might threaten us? And how do we find them before it is too late? This is the challenge that drives the second chapter of post-DART planetary defense, the search for the unknown. As of today, more than 34,000 near-Earth objects have been catalogued. The population of large ones, those over 1 kilometer in diameter, is nearly fully characterized. But the population of smaller objects, those between 100 and 1,000 feet across, remains largely unexplored. And it is this population that poses the most immediate practical threat. A 100-foot asteroid could devastate a city. A 300-foot asteroid could devastate a region. A 600-foot asteroid, slightly larger than Dimorphos, could devastate a small country. And there are estimated to be tens of millions of them, the vast majority unknown and untracked. Current ground-based surveys have inherent limitations that make finding these objects extremely difficult. Asteroids are small, dark, and move against a background of stars. They can only be detected when they reflect sunlight toward Earth, which means they are invisible when they approach from the direction of the Sun. Exactly the situation with the Chelyabinsk impactor in 2013. Ground-based telescopes can only observe at night, cutting their search time roughly in half. Weather, moonlight, and atmospheric turbulence further reduce their effectiveness, and the smallest, most numerous objects are simply too faint to detect until they are already dangerously close. This is why NASA began developing NEO-Surveyor, the Near-Earth Object Surveyor, a dedicated space-based infrared telescope designed to find asteroids by their heat rather than by their reflected light. The concept builds on a remarkable precursor. In 2009, NASA launched the Wide Field Infrared Survey Explorer, or WISE, a space telescope designed to survey the entire sky in infrared light. WISE was not specifically designed for asteroid hunting, but it turned out to be extraordinarily good at it. After its primary mission ended, the spacecraft was repurposed as NEOWISE, the near-Earth object component of the WISE mission, and it spent over a decade scanning for asteroids and comets using its infrared detectors. NEOWISE discovered hundreds of previously unknown near-Earth objects, including several that are classified as potentially hazardous. But NEOWISE was working with aging detectors and a telescope not optimized for the task. It was a brilliant improvisation, not a dedicated solution. NEO-Surveyor is that dedicated solution. The concept is elegant and powerful, Every asteroid, no matter how dark its surface, absorbs sunlight and re-emits it as thermal infrared radiation heat. A telescope sensitive to infrared wavelengths can detect asteroids against the cold background of space, regardless of their albedo or their position relative to the Sun. This is a crucial advantage. Many asteroids are extremely dark. Their surfaces reflect as little as 3 to 5% of the sunlight that falls on them. In visible light, these dark asteroids are nearly invisible against the black background of space. But in infrared, they glow like warm embers against the cold void. NEO-Surveyor's two infrared channels, operating at wavelengths of 4 to 5 micrometers and 6 to 10 micrometers, are optimized to detect this thermal emission. By observing from a point in space called the Sun-Earth L1 Lagrange point, about 1 million miles sunward from Earth, NEO-Surveyor would be able to search regions of sky that are impossible to observe from the ground, including the blind spots near the Sun where incoming threats can hide. The L1 point is particularly well suited for asteroid detection because it provides a vantage point from which the telescope can look outward from the Sun, catching asteroids in their warm phase as they absorb sunlight on their sun-facing sides. NEO-Surveyor was designed to find at least 65% of near-Earth objects larger than 140 meters, roughly 460 feet, within 5 years of beginning operations. That size threshold is significant. An asteroid of 140 meters or larger is capable of causing devastation on a regional or even continental scale. Finding the majority of these objects and determining their orbits would dramatically reduce the risk of a surprise impact. NEO-Surveyor has faced a complicated development history, with budget fluctuations and schedule changes, but it represents a critical next step in building a comprehensive planetary defense architecture. Without a space-based survey, our catalogue of potentially hazardous objects will remain dangerously incomplete. But finding asteroids and deflecting them are two very different problems, and the DART mission, for all its success, tested only one deflection method: the kinetic impactor. What if the kinetic impactor is not enough? What if the threatening asteroid is too large, too close, or too structurally unusual for a simple collision to work? This question drives the third chapter of post-DART planetary defense, the nuclear option. The idea of using nuclear explosives for planetary defense has been debated since the 1960s, but it has always been controversial. The political and ethical objections are obvious. Launching nuclear weapons into space carries immense risks, both real and perceived. The Outer Space Treaty of 1967 prohibits the placement of nuclear weapons in orbit, and while a single defensive detonation might be argued to fall outside the treaty's scope, the geopolitical implications of any nation launching a nuclear-armed rocket are enormous. And yet, physics is unforgiving. For the largest potential impactors, objects a kilometer or more in diameter, a kinetic impactor like DART would be woefully insufficient. To understand why, consider the scale of the problem. Dimorphos has a mass of roughly 4.3 billion kilograms, about 4.7 million tons. DART, at 570 kilograms, changed its velocity by a few millimeters per second. That was sufficient for a body of Dimorphos's size. But a 1-kilometer asteroid has a mass of roughly 1 billion to 2 billion metric tons, hundreds of times more massive than Dimorphos. The same DART-like impact on such a body would change its velocity by a fraction of a micrometer per second. To achieve a meaningful deflection, you would need hundreds or thousands of impactors, launched over decades. The logistics are impractical to the point of impossibility. Nuclear explosives change the equation entirely. A nuclear detonation near the surface of an asteroid does not work the way most people imagine. It is not about blowing the asteroid apart. In the vacuum of space, a nuclear weapon produces no shockwave in the traditional sense. Instead, it generates an intense burst of X-rays and neutrons that irradiate the asteroid's surface, superheating a thin layer of material just a few centimeters deep that then explosively vaporizes and flies off as a jet of hot gas. This vaporized surface material acts like a rocket exhaust, pushing the asteroid in the opposite direction. The momentum transfer from a nuclear standoff detonation, a bomb exploded a few dozen meters above the surface rather than on it, can be hundreds or thousands of times greater than a kinetic impactor of comparable mass. Researchers at Lawrence Livermore National Laboratory and Los Alamos National Laboratory have been quietly studying nuclear deflection for decades. Their computer simulations, using some of the same physics codes originally developed to model nuclear weapons, have explored how different yield weapons, detonation heights, and asteroid compositions affect the momentum transfer. The results consistently show that nuclear standoff detonation is by far the most effective deflection method for large objects. A single well-placed nuclear detonation, with a yield of roughly 1 megaton, could deflect a 500-meter asteroid by a velocity change of several centimeters per second, enough, with a decade of warning, to shift its position by tens of thousands of kilometers at the time of Earth encounter. No other existing technology can match that performance. In 2021, a team at Lawrence Livermore published a study using simulations of nuclear deflection on a Bennu-like rubble pile asteroid. The results showed that even a loosely bound rubble pile could be effectively deflected by a nuclear standoff detonation, as long as the detonation was carefully calibrated to avoid disrupting the body. The key insight was that you do not need to move the whole asteroid as a rigid body. You just need to vaporize enough surface material on one side to create an asymmetric push. The interior can remain largely intact. The simulation showed the asteroid being pushed as a unit, with the vaporized surface layer doing all the work. NAHA and the National Nuclear Security Administration studied this approach in a concept called HAMMER, the Hypervelocity Asteroid Mitigation Mission for Emergency Response. HAMMER envisioned a modular spacecraft that could serve as either a kinetic impactor or a delivery vehicle for a nuclear device, depending on the size of the threat and the available warning time. For small asteroids, the spacecraft itself would serve as the impactor. For larger ones, it would carry a nuclear explosive to the target. The flexibility of the design was intended to address the central uncertainty of planetary defense. You do not know what you are dealing with until you find it. The HAMMER design was deliberately practical. Each spacecraft module would weigh roughly 8.8 metric tons, a mass compatible with current heavy-lift launch vehicles like the SpaceX Falcon Heavy or NASA's Space Launch System. For a small asteroid, a single HAMMER spacecraft launched as a kinetic impactor might be sufficient. For a larger body, multiple HAMMER units could be launched in succession, either as a volley of kinetic impactors or as nuclear delivery vehicles, with each one contributing to the cumulative deflection. The HAMMER study reached sobering conclusions. For an asteroid the size of Bennu, roughly 1,600 feet across, a single kinetic impactor would be insufficient if the warning time was less than about 25 years. Multiple impactors could work with longer warning, but the logistics of launching dozens of spacecraft on short timescales are daunting. To illustrate the scale of the challenge, the study calculated that deflecting a Bennu-sized asteroid with kinetic impactors alone, given only 10 years of warning, would require launching roughly 7.4 HAMMER units every day for several years. That is physically impossible with current launch infrastructure. A nuclear standoff detonation, by contrast, could achieve the same deflection with a single spacecraft and much less warning time. For asteroids significantly larger than Bennu, nuclear deflection was effectively the only viable option. These findings are uncomfortable. They mean that the most effective tool for saving civilization from an asteroid impact is a nuclear weapon, a technology that humanity has spent 70 years trying to contain, control, and ultimately eliminate. The irony is not lost on the scientists who study this problem. The same devices that could end civilization in a nuclear war could save it from an asteroid impact. As Megan Brooks-Sayal, a physicist at Lawrence Livermore, who has led some of the most detailed nuclear deflection simulations ever conducted, has noted, the physics does not care about our politics. It simply tells us what works. And for the largest threats, nuclear deflection works better than anything else. But the political, legal, and technical challenges of developing, testing, and deploying a nuclear planetary defense system are immense. No nuclear deflection device has ever been tested in space. The technology exists in theory and in simulation, but it has never been validated against a real asteroid. And unlike kinetic impact, which DART demonstrated successfully, nuclear deflection may never be testable in a real-world scenario, because detonating a nuclear weapon near an asteroid, even for testing purposes, raises profound questions about the militarization of space, nuclear proliferation, and international law. The fourth chapter belongs to a quieter, more elegant approach, one that trades brute force for patience. The gravity tractor concept was first proposed in 2005 by astronauts Edward Lu and Stanley Love in a paper published in the journal Nature. Lu, a former NASA astronaut who had flown on the Space Shuttle and the International Space Station, brought a unique perspective to the problem. He knew what it felt like to work in space, and he understood the practical constraints of real missions. The idea he and Love proposed is simple in principle but demanding in execution. You fly a massive spacecraft to the vicinity of a threatening asteroid and station it nearby, not on the surface, but hovering a few dozen meters away. The gravitational attraction between the spacecraft and the asteroid creates a tiny but persistent force, pulling the asteroid toward the spacecraft. By carefully positioning the spacecraft on the asteroid, opposite to the direction you want to deflect it, you can slowly, gradually, tug the asteroid off its collision course. To visualize how small this force is, imagine holding a single grain of rice at arm's length. The gravitational pull of your body on that grain of rice is comparable in magnitude to the force a gravity tractor spacecraft would exert on a small asteroid. The force is minuscule, equivalent to the weight of a few grains of sand on Earth, but applied continuously for months or years, without interruption, it accumulates into a measurable change in velocity. Over a decade, a gravity tractor spacecraft massing several tons could shift the velocity of a 200-meter asteroid by roughly half a centimeter per second. That sounds negligible, but over 10 years of orbital travel, that half centimeter per second translates into a positional shift of thousands of kilometers at the time of Earth encounter. The gravity tractor has several advantages over kinetic impact. It is controllable. You can adjust the force by changing the spacecraft's distance or orientation. It is predictable. There is no uncertainty about ejector beta factors or rubble pile physics. It works on any asteroid, regardless of its composition, structure, or spin state, and it is reversible. If the deflection calculation changes, you can reposition the spacecraft and push in a different direction. But it also has a critical weakness. It is slow, extremely slow. A gravity tractor requires years or decades of continuous operation to achieve a meaningful deflection, which means it only works if the threatening asteroid is discovered far in advance. There is another subtle challenge with the gravity tractor that is rarely discussed in popular accounts. The spacecraft must hover near the asteroid without landing on it, and it must do so for years. This means continuously firing its engines to counteract the asteroid's gravitational pull, preventing itself from drifting into the asteroid while simultaneously maintaining its precisely calculated position. The exhaust from these station-keeping thrusters must be directed away from the asteroid, not toward it, or the exhaust plume would push the asteroid in the wrong direction, undoing the gravitational tug. This constraint limits the geometry of the spacecraft and the efficiency of the technique. It is solvable, but it adds complexity to an already demanding mission profile. A related concept, called the ion beam deflection, takes the gravity tractor idea and improves it dramatically. Instead of using gravity alone, the spacecraft fires an ion thruster directly at the asteroid's surface. The stream of charged particles impacts the surface, transferring momentum directly, like a very gentle, very sustained push. Simultaneously, the spacecraft uses its own thrusters to maintain its position relative to the asteroid, compensating for the reaction force of the ion beam. The net effect is a force on the asteroid that is many times larger than gravity alone, potentially reducing the required mission duration from decades to years. Studies have shown that an ion beam deflector could be roughly 10 to 100 times more effective than a gravity tractor of the same mass. The concept was studied in detail by a team at the University of Strathclyde in Scotland, who demonstrated through simulations that even a relatively small ion beam spacecraft could deflect a 100-meter asteroid within a few years of operation. These slow-push techniques are not alternatives to kinetic impact. They are complements. In an ideal planetary defense scenario, multiple approaches would be used in sequence. First, a kinetic impactor would deliver a large initial deflection, changing the asteroid's velocity by a measurable amount. Then, a gravity tractor or ion beam deflector would rendezvous with the target and fine-tune the orbit, correcting for any errors in the initial impact and ensuring the asteroid misses Earth by a comfortable margin. This layered approach provides both the brute force of kinetic impact and the precision of continuous thrusting. It is the planetary defense equivalent of hitting a golf ball hard off the tee and then using a putter for the final approach. Nancy Chabot, the DART coordination lead at the Applied Physics Laboratory, described the philosophy succinctly. The goal is to have multiple tools in the toolbox, because different threats will require different responses, and no single method will work for every scenario. The practical reality, however, is that we have only tested one of these tools. The kinetic impactor DART has been validated against a real asteroid. The gravity tractor exists only in concept studies and computer simulations. The ion beam deflector has never been built, let alone flown. Nuclear standoff detonation has been simulated extensively but never tested in space. And the combined multi-technique approach, kinetic impact followed by gravity tractor fine-tuning, exists only as a theoretical framework. Each of these methods addresses a different part of the threat landscape. Kinetic impactors for small to medium threats with adequate warning. Nuclear devices for large threats or short warning times. Slow push techniques for precision and long-duration operations. The toolbox exists on paper, but only one tool has been taken off the shelf and used. This is why the DART result is both a triumph and a caution. It demonstrated that one deflection method works, but it also revealed, through the unexpectedly large orbital change, that our understanding of asteroids' response is incomplete, and that incompleteness applies equally to all the other methods we have not yet tested. The gravity tractor model assumes a certain gravitational behavior near the asteroid that may not hold for a rubble pile with uneven mass distribution. The nuclear standoff model assumes a certain surface vaporization response that may differ for loosely packed regolith versus solid rock. The ion beam model assumes a certain momentum transfer efficiency that depends on surface properties we have barely characterized. The only way to close these gaps is to keep flying missions, keep testing, keep learning, and keep building the institutional momentum needed to turn a single proof of concept into an operational defense system. The fifth and final chapter of the post-DART era is perhaps the most important of all, and it is the one that receives the least attention. Everything described so far, DART, Hera, Neo-Surveyor, Hammer, the gravity tractor, represents the tools of planetary defense. But tools are useless without a plan. And as of right now, humanity does not have a comprehensive, internationally coordinated plan for what to do when a threatening asteroid is actually found. This problem is not abstract. The planetary defense community has tried to simulate it, and the results have been sobering. Every 2 years, scientists and engineers gather at the International Academy of Astronautics' Planetary Defense Conference to discuss the state of the field. And at several of these conferences, they have conducted elaborate tabletop exercises, fictional scenarios in which a threatening asteroid is discovered, and the participants must decide how to respond. These exercises are designed to be realistic, with plausible asteroid sizes, warning times, and impact probabilities. The participants include representatives from NASA, ESA, the United Nations, and national space agencies around the world. The results have been consistently alarming. In a 2019 exercise conducted at the Planetary Defense Conference in College Park, Maryland, participants were presented with a fictional asteroid on a collision course with Earth with 8 years of warning. Despite having years to prepare, the simulated response was plagued by delays, disagreements, and coordination failures. Different agencies had different risk tolerances. Some advocated for immediate deflection attempts. Others wanted to wait for more orbital data. By the time a consensus was reached, the window for some deflection options had closed. The fictional asteroid struck Denver, Colorado, destroying the city. The exercise was a game. The lessons were deadly serious. A 2021 exercise conducted virtually due to the pandemic, produced equally troubling results. The fictional asteroid in that scenario had only 6 months of warning, far too little time for a deflection mission. The participants concluded that with 6 months' notice, there was essentially nothing that could be done except evacuate the impact zone. An evacuation of a major metropolitan area, while theoretically possible, would involve relocating millions of people with all the logistical, political, and humanitarian challenges that entails. The exercise laid bare a stark reality. Without early detection, decades of warning, not months, even the most capable spacefaring nations would be powerless to prevent a catastrophic impact. Consider the scenario. An asteroid roughly 300 meters across, about 1,000 feet, slightly smaller than the one that created Meteor Crater in Arizona, is discovered on a collision course with Earth, with an estimated impact date 15 years in the future. What happens next? Who decides what to do? Which nation builds the deflection mission? Who pays for it? Who assumes responsibility if the deflection attempt fails, or if it succeeds but redirects the impact from one country to another? What if the asteroid is heading for an unpopulated ocean area? Is deflection still justified, given the risk that a failed attempt could redirect it toward a city? These are not hypothetical questions. They are the questions that the United Nations Committee on the Peaceful Uses of Outer Space has been grappling with for more than a decade. In 2013, the UN General Assembly endorsed the creation of 2 bodies to address the asteroid threat. The International Asteroid Warning Network, which coordinates detection and tracking efforts worldwide, and the Space Mission Planning Advisory Group, which develops deflection mission concepts and provides advice to the UN and national space agencies. These organizations exist. They hold meetings, they publish reports, but they do not have the authority to launch missions, allocate budgets, or make binding decisions. In a real emergency, the critical decisions would fall to individual nations, primarily the United States, which has the most advanced space launch capability and the most mature planetary defense program. There is also the question of who speaks for Earth. When, not if, a threatening asteroid is discovered, the decision to attempt deflection will affect every person on the planet. A successful deflection protects everyone. A failed deflection, or a deflection that goes wrong, could redirect the impact to a different location, potentially trading one disaster for another. The ethical dimensions are staggering. Does a nation that launches a deflection mission have the right to alter the trajectory of a celestial body in ways that could affect other nations? If the deflection shifts the impact point from one continent to another, who bears the moral responsibility? These questions have no easy answers, and they have barely been discussed at the level of international law. The political dimension of planetary defense is often overlooked, but it may be the greatest obstacle of all. Building a spacecraft and launching it at an asteroid is, in the grand scheme of things, a solved problem. DART proved that. The technology exists. The physics works. The engineering is difficult but achievable. What does not exist, not yet, is the political will, the international consensus, and the institutional framework needed to respond to a real threat in time. Planetary defense is a global problem that requires a global response, and global responses are notoriously difficult to organize, especially under pressure, especially when the threat is uncertain, and especially when the costs are measured in billions of dollars. And this is the deepest lesson of the DART mission. The technology worked, the science delivered, the spacecraft hit its target, the orbit changed, but the mission also revealed, with uncomfortable clarity, how much we do not know about asteroids, about our ability to deflect them reliably, and about our readiness to act when the time comes. DART was a triumph, but it was a triumph that illuminated the size of the challenge ahead. And that challenge is not just scientific, it is political, institutional, and ultimately existential. Before we leave the chapters of planetary defense exploration, there is one more development that deserves attention, one that connects directly to the Apophis scare of 2004 and illustrates just how quickly the field is evolving. Remember Apophis, the asteroid that briefly terrified the world with its estimated 2.7% chance of hitting Earth in 2029. That impact was ruled out years ago. But Apophis will still make an extraordinarily close approach to Earth on April 13th, 2029, passing within roughly 19,800 miles of the surface. That is closer than the orbits of geostationary satellites. It is closer than any asteroid of that size has come in recorded history. On that date, Apophis will be visible to the naked eye from parts of Europe, Africa, and Western Asia, a slowly moving point of light drifting across the sky, a rock the size of 3 football fields, passing closer to Earth than any object of its kind in modern memory. This close approach is not a threat, but it is an opportunity, perhaps the greatest opportunity in the history of asteroid science. For a few hours, a potentially hazardous asteroid will be close enough to study with unprecedented detail. Ground-based radar can map its shape to a resolution of a few meters. Telescopes can measure its composition, its rotation rate, its thermal properties, and if a spacecraft were positioned nearby, it could study Apophis in ways that are normally impossible, measuring its mass, probing its interior, observing how Earth's gravity reshapes its surface as it passes through the tidal field of our planet. NASA is sending a spacecraft to do exactly that. The mission, originally called OSIRIS-APEX, a repurposed version of the OSIRIS-REx spacecraft that returned samples from Benn in 2023, is being redirected to rendezvous with Apophis shortly after its close Earth approach in 2029. It will orbit Apophis for 18 months, mapping its surface and studying how the flyby changed it. Earth's gravity during the close approach is expected to trigger surface disturbances, landslides, seismic shaking, changes in rotation, that will provide a natural experiment in asteroid geophysics. The mission will give scientists a close-up look at a potentially hazardous asteroid's response to gravitational stress, complementing DART's data on response to kinetic stress. The Apophis flyby itself will be a moment of extraordinary scientific and public drama. On the evening of April 13th, 2029, observers in Europe and Africa will be able to step outside, look up, and watch a bright point of light drift slowly across the sky. An asteroid larger than the Eiffel Tower is tall, passing closer to Earth than many communications satellites. For a few hours, the reality of the asteroid threat will not be abstract or statistical. It will be visible, it will be tangible, it will be a rock in the sky, close enough to see without a telescope, a reminder that our neighborhood in space is not as safe as it seems. Whether this visibility translates into sustained public and political support for planetary defense remains to be seen. But the opportunity is unprecedented. The convergence of DART, Hera, and the Apophis encounter represents a golden era for asteroid science, a period in which humanity will have visited, impacted, and closely observed multiple near-Earth asteroids within a single decade. The data from these missions will transform our understanding of small bodies, and by extension, our ability to defend against them. Each mission fills a different gap in our knowledge. DART tested kinetic impact. Hera will examine the aftermath. The Apophis encounter will study a real potentially hazardous asteroid during a real close approach. Together, they form the foundation of a planetary defense capability that is no longer theoretical but empirical, built on data, not on guesswork. And yet, even with all of this progress, there are scenarios that keep planetary defense scientists awake at night. What if we discover a threatening asteroid with only months of warning rather than years? What if the threatening asteroid is a dark object, one with a surface so non-reflective that it escapes detection until it is very close? What if the threat comes not from a single large asteroid, but from a swarm of smaller fragments, the result of a larger body breaking apart under tidal stress or after a collision in the asteroid belt? For these worst-case scenarios, the planetary defense community has begun exploring the concept of rapid response missions. Spacecraft that could be launched within months of a threat being identified, rather than the years that DART required. The idea is to maintain one or more deflection vehicles in a state of readiness, either on the ground or in orbit, ready to be launched on short notice. This is analogous to maintaining a fire department. You do not build the fire truck after the fire starts. You build it in advance and keep it ready. The technical challenges are significant. Spacecraft deteriorate during storage, Launch vehicles must be available on short notice, and the navigation algorithms must be flexible enough to accommodate a wide range of targets and trajectories. But the concept is sound, and it represents the logical next step beyond one-off demonstrations missions like DART. One proposal, studied by researchers at the Massachusetts Institute of Technology, envisions a constellation of small kinetic impactor spacecraft maintained in high Earth orbit, ready to be dispatched toward a newly discovered threat within weeks. Each spacecraft would be relatively modest in size, perhaps a few hundred kilograms, but launched in salvos, multiple impactors could deliver cumulative momentum changes to a small asteroid even with very short warning times. The MIT study calculated that a constellation of 5 to 10 spacecraft, maintained at a cost comparable to a mid-range weather satellite program, could provide a meaningful rapid response capability against asteroids up to roughly 150 meters in diameter. Another approach, studied at the Jet Propulsion Laboratory, would use the emerging generation of small launch vehicles, rockets like those built by companies like Rocket Lab and Relativity Space, to enable rapid, low-cost launches tailored to specific threats. Instead of waiting for a slot on a large, expensive rocket, a planetary defense impactor could be launched on a dedicated small vehicle within weeks of a threat being confirmed. The flexibility and availability of small launchers could transform the response timeline from years to months. These ideas remain on paper for now, but they illustrate a crucial evolution in thinking about planetary defense. A shift from one-off demonstrations to operational readiness, from proving that deflection is possible to ensuring that deflection is available when it is needed, on whatever timeline the universe dictates. The question is no longer whether we can move an asteroid. We can. The question is whether we will be ready when we need to. There is a moment, late at night, when the mind stops calculating and starts feeling. It is the moment when the numbers fade and the meaning arrives. And the meaning of the DART mission, the real meaning, the one that lives beneath the engineering and the physics and the orbital mechanics, is something that most people never think about. But once you see it, you cannot unsee it. Consider what happened on September 26, 2022. A species that has existed for roughly 300,000 years. A blink of an eye in the 4.5 billion year history of the solar system, built a machine, launched it into the void, and deliberately altered the orbit of a celestial body. That had never happened before. Not in the history of Earth, not in the history of the solar system, not as far as we know, in the history of the universe. For 4.5 billion years, asteroids moved in orbits determined solely by gravity, collisions, and the slow push of sunlight. Their paths were set by physics and chance. And then, for the first time, one of those paths was changed by intention. Let that sink in. We are accustomed to thinking of humanity as powerless against the cosmos, and in most ways, we are. We cannot stop the sun from expanding into a red giant in 5 billion years. We cannot prevent the Andromeda galaxy from colliding with the Milky Way in 4.5 billion years. We cannot reverse the expansion of the universe or halt the slow march of entropy toward heat death. The forces that govern the cosmos are vast beyond comprehension, and we are, in the face of them, impossibly small. But DART proved something that matters. It proved that we are not entirely helpless. In one narrow but critical domain, the domain of asteroid impacts, we have the beginnings of a capability to defend ourselves. Not against everything. Not against the largest threats. Not with current technology. Not without years of warning. But against some threats, in some circumstances, with enough time and enough preparation, we can act. We can reach out across millions of miles of empty space and change the future. This is not science fiction. This is something that actually happened. A spacecraft built by human hands, guided by human mathematics, powered by human ingenuity, crossed the inner solar system and pushed a rock. And the rock moved. There is a paradox at the heart of this achievement that is worth sitting with. We are, as far as we know, the only conscious beings in the observable universe. That claim is provisional. We may discover evidence of extraterrestrial intelligence tomorrow. But, as of this moment, in this conversation between narrator and listener, we know of exactly one species in the cosmos that can contemplate its own extinction and take steps to prevent it. One species among the estimated 8.7 million on Earth, one planet among the trillions in the observable universe. The consciousness that built DART, the ability to imagine the future, to calculate trajectories, to design machines, to coordinate the actions of thousands of people toward a common goal, may be the rarest phenomenon in the cosmos. More rare than pulsars, more rare than black holes, more rare than the heaviest elements forged in neutron star collisions. Consciousness itself may be the universe's greatest anomaly, and yet that anomaly is housed in bodies that are staggeringly fragile. A few degrees of temperature change and we die. A few minutes without oxygen and we die. A rock from space, no larger than a football stadium, striking at cosmic speed, and the civilization that houses this consciousness could be shattered. The contrast between the extraordinary nature of what we are and the ordinary physics of what can destroy us is one of the most unsettling truths in all of science. The existential weight of this achievement is easy to miss if you focus only on the numbers. 33 minutes off the orbital period, a beta factor of 3.6, an ejector mass of 10 million kilograms. These are important numbers, they are the currency of science, but they are not the meaning. The meaning is this: for 66 million years, since the last great impactor struck the Earth and ended the age of dinosaurs, life on this planet has been vulnerable to the same fate. Every species that has lived and died in those 66 million years, every mammal, every bird, every fish, every insect, existed under a sky that could, at any moment, deliver another killing blow. None of them knew it. None of them could have done anything about it. They were passengers on a planet hurtling through a debris field, with no steering wheel and no brakes. And then, in the span of a few thousand years, an interval so short that it barely registers on geological timescales, one species among millions figured out what asteroids are, learned to track them, and built a machine to push them away. There is something almost unbearably poignant about that. We are the first beings in the history of this planet who understand the threat and have even the rudimentary ability to respond to it. Every dinosaur that ever lived, every trilobite that crawled the ocean floor, every creature that perished in the 5 great mass extinctions of Earth's past, none of them had this. They were subject to the indifference of physics. We are the first to push back, and yet we must be careful not to let this achievement breed complacency, because there is a dimension to the DART story that is rarely discussed, one that connects the physics of asteroid deflection to the deepest questions about what we are and where we come from. Every atom in your body was forged inside a dying star. The carbon in your muscles, the calcium in your bones, the iron in your blood, all of it was cooked in the nuclear furnace of a star that lived and died billions of years before the sun was born. When that star exploded as a supernova, it scattered those atoms across light years of space. They drifted through interstellar clouds. They were swept up by the gravitational collapse that formed our solar system 4.5 billion years ago. Some of those atoms ended up in the sun, some ended up in Earth, some ended up in the asteroids. This means that you and Dimorphos are made of the same stuff, the same ancient stardust, the same atoms forged in the same stellar furnaces. The rocks that threaten us are not foreign invaders. They are our cousins, assembled from the same raw materials, in the same solar nebula, at roughly the same time. The only difference is that some of that material fell together to form a planet with liquid water and an atmosphere and, eventually, life, and the rest remained as rubble, cold, airless, tumbling through the void. When DART struck Dimorphos, it was, in a sense, one arrangement of stardust colliding with another. The fact that one of those arrangements had achieved consciousness, had developed mathematics and engineering, and the will to shape its own future, is either the most extraordinary thing in the universe or the most ordinary. We do not yet know which. And that uncertainty is itself one of the deepest mysteries that the DART mission, in its quiet way, touches upon. Are we alone? Is intelligence common in the cosmos, or vanishingly rare? Have other civilizations faced the same threat from their own local rubble? And if so, did they develop the capability to defend themselves? Or did they perish silently without a trace, struck by the indifferent mechanics of their own solar systems before they could reach the stars? We do not know. We may never know. But the DART mission represents one possible answer to a question that the cosmos poses to every intelligent species. Can you survive your own neighborhood? The answer for now is maybe. We have proven that we can push a small asteroid under controlled conditions with years of preparation. We have not proven that we can deflect a large asteroid under emergency conditions with months of warning. We have not proven that our models are reliable enough to predict the outcome of a deflection attempt with the precision that real-world scenarios demand. And we have not built the institutional and political infrastructure needed to respond to a genuine threat at the speed that physics requires. But what DART did prove is that the effort is not futile. That is no small thing. For most of human history, the asteroid threat was invisible, unknown, and entirely beyond our control. Now it is visible, tracked, and at least in principle, within our control. The transition from helplessness to agency, from ignorance to awareness, from passivity to action, is one of the most important transitions in the history of our species. It ranks alongside the development of agriculture, the invention of writing, and the discovery of antibiotics as a moment when humans fundamentally changed their relationship with the forces that could destroy them. The difference is that this time the force is cosmic. It is not a disease, or a famine, or a war. It is a rock from space, moving on an orbit determined by the laws of gravity and chance. And the fact that we have begun, tentatively, imperfectly, with massive gaps in our knowledge and our readiness, to develop the capability to redirect such a rock is a testament to something deep in our nature. Call it curiosity, call it stubbornness, call it the refusal to accept that the universe is allowed to end us on a whim. But with that capability comes a burden, because now that we know the threat exists, and now that we know, at least in principle, how to counter it, the failure to prepare becomes not a misfortune but a choice. The dinosaurs had no choice. They could not have built a DART mission. They could not have tracked the Chicxulub impactor. They went extinct because the universe is random and they were unlucky. If we go extinct from an asteroid impact, the reason will be different. It will not be because we did not know. It will not be because we could not act. It will be because we chose not to prepare. Let that sink in. The philosopher Carl Sagan, who spent much of his career advocating for planetary defense, captured this tension with characteristic clarity. He wrote that our species lives on a mote of dust suspended in a sunbeam, a planet that is vanishingly small and vanishingly fragile in the vastness of space. But he also argued that this fragility is precisely what makes the effort to protect it meaningful. We are rare. Intelligence is rare. The ability to understand the universe and to act within it, to move asteroids, to predict impacts, to shape our own fate, may be extraordinarily rare in the cosmos. If we are the only beings in this galaxy who can do these things, then the loss of our civilization is not just a tragedy for us, it is a tragedy for the universe itself. Sagan also understood the duality at the heart of planetary defense. The fact that the same knowledge and technology that allows us to deflect asteroids could, in the wrong hands or the wrong circumstances, be used to redirect them toward a target. He wrestled with this problem for years, warning that asteroid deflection technology is inherently dual use. A spacecraft capable of pushing a dangerous asteroid away from Earth is also, in principle, capable of pushing a harmless asteroid toward Earth. This is not a reason to abandon the technology. The threat is real, and the capability is necessary. But it is a reason to develop it carefully, transparently, and under international oversight. The power to move worlds is a power that must be wielded with extraordinary responsibility. There is a deeper philosophical layer still. Consider the relationship between Dimorphos and humanity from the perspective of the asteroid. Dimorphos existed for billions of years, orbiting Didymos in silence, unobserved, unnamed, undisturbed. It was a piece of the solar system's furniture, unremarkable, unnoticed, untouched. And then, after 4.5 billion years of solitary existence, it was struck by a machine launched by beings it had never known existed. Dimorphos did not choose to participate in DART. It had no say in the matter. It was an object, acted upon, not acting. And yet, in being struck, it became the most important asteroid in human history. It became a symbol of something that transcends its own existence. The moment when life on Earth began to shape the solar system, rather than merely being shaped by it. This is the deeper truth of the DART mission. It is not just about planetary defense. It is about what kind of species we are and what kind of species we choose to be. Are we the kind that sees a threat and acts, or are we the kind that sees a threat and looks away? DART's success suggests the former, but a single successful test is not a defense system. It is a proof of concept. The gap between a proof of concept and a functioning defense, one that can respond to a real threat on a real timeline with real consequences, is enormous. And bridging that gap requires not just better technology, but better institutions, better coordination, and a sustained commitment to a problem that on most days seems abstract and distant. There is a thought experiment that planetary defense scientists sometimes use to illustrate the stakes, and it is worth sharing because it puts everything in perspective. Imagine compressing the entire 4.5 billion year history of Earth into a single 24-hour day. At midnight, the Earth forms. The first simple cells appear around 4 in the morning. For most of the day, from dawn through midday, through the afternoon, through dinner, life remains microscopic. Complex multicellular life does not appear until roughly 8:30 in the evening. The dinosaurs arrive around 10:40 p.m. and go extinct at approximately 11:39 p.m., killed by the Chicxulub impactor. The entire history of our species, from the first Homo sapiens to the DART mission, occupies the last 1.7 seconds of the day, less than 2 seconds. In those 2 seconds, we went from sharpening stones to deflecting asteroids. In those 2 seconds, we developed language, mathematics, agriculture, cities, telescopes, rockets, and the ability to predict and alter the orbits of celestial bodies. The sheer acceleration of our capabilities is unlike anything else in the 4.5 billion year history of this planet. Nothing else, no other species, no other process, no other force, has ever done what we have done in such a vanishingly short time, and that is both our greatest strength and our greatest vulnerability. We are powerful enough to move asteroids, but fragile enough to be killed by them. We are intelligent enough to predict impacts decades in advance, but foolish enough to underfund the programs that do the predicting. We are capable of extraordinary cooperation. DART involved scientists and engineers from dozens of countries, and equally capable of extraordinary short-sightedness. The difficulty is that asteroid impacts are the wrong kind of threat for human psychology. They are low probability, high consequence events, the kind that our brains are worst at evaluating. We are wired to respond to immediate, visible, personal dangers. A predator in the grass, a fire in the building, a car swerving into our lane. We are not wired to respond to dangers that may or may not materialize in our lifetimes, even if the consequences would be catastrophic. This is the same cognitive bias that makes climate change so difficult to address politically, and it applies with equal force to asteroid impacts. The Chelyabinsk event in 2013 briefly focused the world's attention on the asteroid threat. For a few weeks, politicians spoke urgently about increasing funding for detection and deflection. News networks ran specials, experts were interviewed, and then the attention faded. Other crises took over. The funding increased modestly, but fell far short of what scientists had recommended. The pattern is depressingly familiar. A dramatic event captures attention. The attention generates concern. The concern generates talk, and the talk, eventually, fades into silence. DART broke this cycle, at least partially. By demonstrating a real deflection capability, it moved the conversation from theory to practice. It is no longer possible to say that asteroid deflection is purely hypothetical. It has been done. A spacecraft hit an asteroid, and the asteroid moved. That fact, demonstrated, measured, confirmed, gives planetary defense advocates something that theories and simulations never could: proof. And proof is the currency of political action. But proof alone is not enough. The DART mission cost approximately $325 million, a bargain by space mission standards, roughly the cost of a single advanced fighter jet. The Hera mission cost approximately €363 million. NEO Surveyor, if fully funded and launched on schedule, will cost roughly $1.2 billion. These are not large numbers by the standards of national defense budgets, which in the United States alone exceed $800 billion per year. The cost of building a comprehensive planetary defense system, including a space-based telescope for detection, a fleet of ready-to-launch deflection vehicles, and the ground infrastructure to coordinate everything would be a tiny fraction of what the world spends on military forces designed to counter threats from other humans. The irony is sharp. We spend hundreds of billions defending against threats from our own species, but only a few 100 million defending against threats from the cosmos. The asteroid that killed the dinosaurs did not care about national borders, military alliances, or geopolitical tensions. It struck with the democratic indifference of physics, killing everything equally. The next one will be no different, and there will be a next one. The solar system has not run out of asteroids. The gravitational dynamics that send rocks careening through the inner solar system have not stopped. The probability of a significant impact in any given century is low, but it is not zero. And over the timescales that civilizations aspire to endure, centuries, millennia, longer, the cumulative probability approaches certainty. If we survive long enough, we will face another large impact. The only question is whether we will be ready. There is a strange and beautiful irony embedded in this entire story. The asteroids that threaten us are also the asteroids that made us. The heavy elements that form the core of our planet, the iron, the nickel, the gold, the platinum, were delivered in part by asteroid and comet impacts during the first billion years of Earth's history, a period of intense bombardment called the Late Heavy Bombardment. The water in our oceans may have been delivered by comets and water-rich asteroids. The organic molecules that seeded the first life may have arrived on meteorites. We are, in a very real sense, the children of the bombardment. The same process that threatens to destroy us is the process that created the conditions for our existence. The rocks are not our enemies. They are the universe's building blocks, rearranged by time and chance into configurations that are sometimes beautiful, sometimes habitable, and sometimes deadly. Dimorphos is not a villain. It is a piece of the solar system's history, a fragment of the original nebula that collapsed to form the Sun and planets 4.5 billion years ago. It has been orbiting the Sun in silence ever since, following the laws of physics with mathematical precision, until one day a species on a nearby planet decided to reach out and push it. That push, Dart's push, changed the orbit of Dimorphos by 33 minutes. In the grand scheme of things, 33 minutes is nothing. The solar system is 4.5 billion years old. 33 minutes is to that time scale what a single heartbeat is to a human lifetime. But it was a deliberate heartbeat, an intentional one, and in a universe governed by blind physics and random chance, intention is the rarest thing of all. The DART mission gave us reason to hope that the answer is yes, that we can be ready, that we can act, that we can defend our small corner of the cosmos against the debris that fills it. It showed that the technology works. It showed that international cooperation on planetary defense is possible. It showed that a small, focused team of engineers and scientists can accomplish something that, a generation ago, was the stuff of science fiction movies, deliberately moving an asteroid. But it also showed us the limits of our knowledge. The 33-minute orbital change, so far beyond predictions, was a gift and a warning. A gift because it showed that kinetic impact is more effective than we thought. A warning because it showed that our models are less accurate than we believed. And in the real-world scenario of a threatening asteroid approaching Earth, accuracy matters. Overconfidence is as dangerous as ignorance. Deflecting an asteroid by too much, or in the wrong direction, or at the wrong time, could create a new collision instead of preventing one. The margin between success and catastrophe is razor thin, and it depends on understanding the target with a precision that we do not yet possess. Consider what this means on a personal level. Right now, as you listen to this, there are asteroids crossing Earth's orbit that have not yet been discovered. Some of them are small, pebbles and boulders that would burn up harmlessly in the atmosphere. Some of them are larger. The vast majority will never come close enough to worry about. But somewhere in the dark, drifting on an orbit shaped by billions of years of gravitational interactions, there may be a rock with our name on it, and we might not find it for years, or decades, or, in the worst case, not until it is too late. This is not a reason to panic. The probability of a civilization-threatening impact in any given year is extraordinarily low, but it is a reason to act, to invest, to prepare. to treat planetary defense not as a luxury or a curiosity, but as what it actually is, an insurance policy against extinction. The DART mission was the first premium payment on that insurance policy. It was small, it was preliminary, it covered only a fraction of the risk. But it was real, and it proved that paying the premium is possible. Think about what an insurance policy against extinction actually means. It means accepting that the universe is not benign. It means acknowledging that the long-term survival of our species is not guaranteed by any law of nature, any divine promise, or any technological trajectory. It means looking at the night sky, not just with wonder, but with a certain hard-eyed realism. The same realism that drives any prudent person to insure their home against fire, even though fires are rare. The difference is the scale. A house fire affects a family. An asteroid impact can affect a civilization. And the cost of the insurance, a few $1 billion spread across decades, shared among the nations of the world, is vanishingly small compared to the value of what it protects. The total economic output of human civilization is roughly $100 trillion per year. A comprehensive planetary defense system would cost a fraction of 1% of that. We insure ourselves against far less likely events. Earthquake insurance in regions that have not experienced a major quake in centuries, flood insurance for areas above the 100-year floodplain. And we do so because we understand that low probability does not mean no probability. The same logic applies to asteroid impacts, with the added consideration that the consequences of being uninsured are not just financial, they are existential. The question now is whether we will keep paying, whether we will build on DART's success with the sustained investment and institutional commitment that the threat demands. This is why Hera matters. This is why Neo Surveyor matters. This is why continued investment in astroscience, in numerical modeling, in laboratory experiments, in spacecraft missions, all of it matters. Not because the threat is imminent, not because the sky is falling, but because the window between discovering a threat and being able to respond to it is measured in years, and the work of preparation must be done in advance. By the time you see the asteroid coming, it is too late to start building the mission. The ships must be ready, the plans must be in place, the knowledge must already exist. The universe does not care about our preparations, our politics, or our priorities. It operates on physics, not on intention. The asteroids will continue to orbit the Sun, crossing Earth's path on their ancient trajectories, whether we are watching or not, whether we are ready or not, whether we survive or not. The cosmos is indifferent to our existence. It will continue without us, as it continued without the dinosaurs, as it continued without the trilobites, as it will continue long after the last star burns out and the universe goes dark. But we are not indifferent. We care, we notice, we measure and model and build. And on one day in September of 2022, we pushed back against the indifference of the cosmos and moved a rock. It was a small rock. It was a small push, but it was the first. We are not there yet, but for the first time in the history of our species, we are on the path. Step back for a moment from the data. Step back from the orbital mechanics, the beta factors, the ejector plumes, and the mission timelines. Step back from the numbers and the names and the acronyms, and look at the whole story from a distance. Look at what it means. Not for science, for us. We began this journey with a rock, a small, unremarkable moonlet orbiting a small, unremarkable asteroid in a solar system full of small, unremarkable objects. Dimorphos had no special significance before DART. It was not dangerous. It was not beautiful. It was not even visible to the naked eye. It was a piece of cosmic debris, left over from the formation of the solar system, following the same orbit it had followed for billions of years. And then, in the span of a few years, it became the most important rock in human history, not because of what it is, but because of what we did to it. The DART mission changed our relationship with the cosmos. Before DART, humanity was a passenger, riding a planet through a universe we could observe but not influence. We could watch asteroids. We could track them. We could name them and classify them and calculate their orbits to extraordinary precision. But we could not touch them. We could not move them. We were observers, cataloguers, measurers, never actors. DART changed that. On September 26, 2022, we became actors. We reached out across 7 million miles of empty space and deliberately changed the trajectory of another world. The change was small, 33 minutes off an orbital period, but the principle was enormous. For the first time, a living being on planet Earth reshaped the solar system on purpose. The implications of that moment extend far beyond planetary defense. They touch on the deepest questions about our role in the universe and the future of our species. Remember the image from the opening of this story. Something the size of a small city, hitting the Earth at 43,000 miles per hour, ending the age of dinosaurs in a single catastrophic instant. That image haunts the planetary defense community because it is not a myth. It is a geological fact, recorded in the rock record of every continent, confirmed by the crater in the Yucatan, supported by the iridium layer at the Cretaceous-Paleogene boundary. It happened. It can happen again. And the DART mission is the first step, the very first step, in ensuring that the next time it happens, the outcome is different. Not because physics has changed, but because we have. Consider the timescales involved. The solar system is 4.5 billion years old. Human civilization, the organized technological civilization that built DART, is roughly 10,000 years old. That is a ratio of 450,000 to 1. If the solar system's history were represented by a road stretching from New York to Los Angeles, the entire history of human civilization would occupy the last 29 feet. And the period during which we have had the capability to detect and deflect asteroids, roughly the last 30 years, would occupy less than 1/10 of an inch at the very end of the road. We are newcomers here. Spectacularly, incomprehensibly new. The universe has been running its experiments for billions of years without our input or our awareness. Stars have formed and died. Galaxies have collided and merged. Asteroids have struck planets millions of times, reshaping surfaces, extinguishing species, creating new conditions for life. And through all of it, no one was watching, no one was calculating, no one was trying to change the outcome. The universe just ran, blindly, following its laws, indifferent to whether anything alive was caught in the gears. And now, in the last fraction of the last second of this immense history, something new has appeared. A species that watches, that calculates, that builds machines to change outcomes, that refuses to accept extinction as the default. The question of what this means for our future is one that no amount of data can fully answer, but the outlines are becoming visible. In the near term, the next few decades, the implications are practical. DART success will accelerate the development of planetary defense capabilities. HERA will refine our understanding of asteroid interests. NEO-Surveyor, if funded and launched on schedule, will catalogue the majority of the remaining undiscovered threats in the 140-meter size range. The Apophis flyby in 2029 will provide an unprecedented opportunity to study a potentially hazardous asteroid up close, and the ongoing work of ground-based surveys will continue to expand the catalogue of known near-Earth objects, gradually closing the blind spots in our awareness. In the medium term, the next century, a comprehensive planetary defense system could become operational. A space-based survey telescope continuously scanning for threats. A fleet of ready-to-launch deflection vehicles, maintained in readiness like the missiles in a nuclear deterrent. International agreements defining the decision-making process for deflection missions. Backup strategies for short warning scenarios. This is not a fantasy. Every component of such a system exists in some form today. The technology is available. The science is understood. What is needed is the political will to build it and the institutional framework to operate it. Imagine what that system would look like. Telescope deep space, positioned at the Sun-Earth L1 Lagrange point, scanning the sky continuously in infrared, finding asteroids by their warmth. Ground-based radar stations tracking known objects with millimeter precision, constantly refining their orbits. A network of observatories, both professional and amateur, monitoring the near-Earth environment around the clock. And at the center of it all, a mission planning hub, an international facility, staffed by engineers and scientists from every major space agency, maintaining a library of pre-designed deflection missions that can be customized and launched within months of a threat being confirmed. The kinetic impactors would be built, tested, and stored in a state of readiness. The nuclear deflection option would be studied, simulated, and, if the political will could be summoned, held in reserve for the largest threats. The gravity tractors and ion beam deflectors would be ready for precision correction after the initial impact. This system would cost billions of dollars to build and maintain, but spread across the nations of the world, across decades of operation, the cost per person would be negligible, less than the cost of a cup of coffee per year. For that price, humanity would buy something that no other species has ever possessed: the guarantee that the sky will not fall without warning, and the capability to push back if it tries. In the longer term, centuries, millennia, the implications become truly profound. A species that can deflect asteroids is a species that can, in principle, reshape its entire solar system. The same technologies that push a rock out of the way can push a rock into a useful orbit, capturing asteroids for mining, redirecting comets to deliver water to Mars, clearing debris from orbital pathways. The boundary between planetary defense and planetary engineering is not as sharp as it might seem. The skills are the same. The physics is the same. The only difference is the motivation. This is where the DART story connects to a much larger narrative, the narrative of humanity becoming a truly spacefaring civilization. For the moment, we are a species that has dipped its toes into space. We have orbited our planet. We have walked on our moon. We have sent robots to our neighbors. But we have not yet settled space. We have not yet built the infrastructure, the economy, or the civilization that would make us resilient against the thousand threats that could end us. Asteroid impacts, supervolcanic eruptions, pandemics, climate catastrophe, self-inflicted nuclear war. DART is a single step toward that resilience, a small step, a tentative step, but a real one, and the direction it points is clear, outward, into the solar system, to a future in which we are not trapped on one fragile world, hoping that the sky does not fall, but spread across multiple worlds, capable of surviving whatever the universe throws at us. That future is not guaranteed. It may never arrive. The challenges are immense: technical, economic, political, existential. But the DART mission proved that the first challenge, the challenge of moving the rocks in our path, is solvable. We can do it. We have done it. And that is enough to keep going. There is one more reflection that deserves space before we close, and it concerns not the future, but the present. Not what DART means for the centuries ahead, but what it means for tonight, for this moment, for the person listening to these words in the dark, perhaps on the edge of sleep, perhaps staring at the ceiling, perhaps looking out a window at the stars. The DART mission was built by roughly 300 people at the Johns Hopkins Applied Physics Laboratory, in collaboration with scientists and engineers from dozens of institutions around the world. 300 people. That is roughly the population of a small apartment building, a tiny, almost invisible fraction of the 8 billion people who share this planet. And those 300 people, working with budgets smaller than what some cities spend on a single sports stadium, built a machine changed the orbit of a world. This fact should haunt us, not because it is frightening, because it is hopeful. It demonstrates that extraordinary things can be accomplished by small groups of dedicated people working on problems that matter. It demonstrates that the resources exist, the knowledge exists, the talent exists. What is sometimes lacking, what is always the hardest thing to summon, is the collective decision to act, to say this matters, to say the future of our species is worth protecting, to say the sky is not guaranteed to remain clear, and we should prepare for the day it is not. The opening of this story began with the Chicxulub impact, a rock the size of a small city ending the age of dinosaurs. The closing of this story begins with a different image, a spacecraft the size of a vending machine, launched by a species that has existed for an eye blink of cosmic time, crossing the inner solar system to push a rock the size of a stadium. The contrast between those two images is the story of human progress, from being subject to the violence of the cosmos, to beginning, tentatively, imperfectly, with enormous gaps in our readiness, to resist it. We are at the very beginning of this journey. The road ahead is long, uncertain, and full of threats we have not yet discovered, and challenges we have not yet imagined. But the first step has been taken. The first rock has been moved, and the knowledge that it can be done, that we are not powerless, that the laws of physics are our tools as much as our constraints, is the most important knowledge we have gained from this entire mission. Not the beta factor, not the orbital period change, not the ejector mass or the crater depth. The most important thing DART gave us is the certainty that we can act, that when the universe sends a rock toward our home, we do not have to sit and watch it fall. The transition from reflection to resolution begins here. We have looked at the whole story. We have seen the science, the engineering, the politics, the philosophy. We have measured the scales and counted the costs and confronted the uncertainties. And now, in the quiet space at the end of this journey, we come to the part that matters most, the answer. When we started tonight, we asked a question that sits at the intersection of physics, engineering, and survival. Can we defend our planet against an asteroid impact? Can we take the single most catastrophic natural disaster in the history of life on Earth, the kind of event that wiped out 75% of all species 66 million years ago, and prevent it from happening again? The answer, after everything we have explored, is yes, with qualifications, with caveats, with the humility that honest science demands. But yes, DART proved that a kinetic impactor can change the orbit of an asteroid, not in theory, not in simulation, in reality. A spacecraft weighing roughly 1,250 pounds, travelling at nearly 14,000 miles per hour, struck a moonlet the size of a football stadium and shortened its orbital period by 33 minutes. The change was more than 25 times the minimum prediction. The physics works, the engineering works. The concept of kinetic impact as a planetary defense tool has been validated against a real asteroid, under real conditions, with real measurements confirming the result. But DART also proved that our understanding is incomplete. The unexpectedly large orbital change, driven by massive ejecta from a loosely packed rubble pile, showed that our models of asteroid interiors are less accurate than we believed. This matters because accuracy is not optional in planetary defense. Deflecting an asteroid by too much is not the same as deflecting it by just enough. In the real-world scenario of a threatening impactor, the margin between salvation and disaster depends on knowing, with precision, how the target will respond, and we do not yet have that precision. This is why the story does not end with DART. It continues with Hera, which will examine the aftermath of the impact and provide the close-up data needed to calibrate our models. It continues with Neo Surveyor, which will search for the thousands of potentially hazardous asteroids that remain undiscovered. It continues with the Apophis encounter, which will give us our most detailed look yet at a real potentially hazardous asteroid. And it continues with the ongoing, unglamorous work of tracking, modeling, and preparing, the day-to-day effort of a small community of scientists and engineers who carry the weight of a civilization-scale responsibility on budgets that would not cover a mid-tier Hollywood film. The core message of the DART mission is this: the universe is not safe, but we are not helpless. We live in a solar system full of debris, on a planet that has been struck catastrophically in the past and will be struck again in the future. But we are the first species in the 4.5 billion year history of this planet that has the knowledge to predict the threat and the technology to prevent it. That is new. That has never existed before, and it changes everything. The universe, in its vast indifference, does not care whether we survive. It did not care when the dinosaurs died. It will not care if we die. The asteroids follow their orbits. Gravity pulls. Objects collide. This is the way the cosmos has operated for billions of years, and it will continue to operate this way long after every trace of human civilization has been erased by time. We are an anomaly in a universe that runs on blind mechanics, a flicker of awareness in an otherwise unconscious machine. But that flicker matters. It matters because awareness is the prerequisite for action, and action is the prerequisite for survival. The dinosaurs were aware, in their way. They saw the sky, felt the ground, responded to their environment. But they were not aware in the way that counts for planetary defense. They could not predict. They could not plan. They could not build. We can. And the DART mission was the proof. If you remember nothing else from tonight, remember this: a rock the size of a football stadium, orbiting the sun in cold silence for billions of years, was struck by a machine built by a species that has existed for less than 1% of 1% of the solar system's lifetime. And the rock moved. It moved more than anyone expected. It moved because physics works the same way at the scale of a vending machine as it does at the scale of a world. And it moved because a small community of human beings decided that the fate of their planet was worth fighting for. Dimorphos will continue to orbit Didymos, as it has for eons. Its orbit is slightly different now, 33 minutes shorter, a hair more eccentric, carrying the faint signature of a human decision imprinted on the geometry of space. Hera will arrive soon, and it will see what Dart left behind, the crater or the reshaping or whatever the impact carved into that fragile surface. And the data it returns will make the next mission better, more precise, more confident. Somewhere out there, beyond the reach of our telescopes and surveys, there are asteroids we have not yet found. Some of them are on orbits that will one day bring them close to Earth. Most will miss by comfortable margins. A few will come close, and perhaps one, at some point in the centuries or millennia ahead, will be aimed at us. When that day comes, the response will trace its lineage directly back to a small spacecraft that launched from Vandenberg, California in November of 2021 and died on purpose against the surface of a moonlet in September of 2022. Dart was not a weapon, it was a test, a rehearsal. The first rehearsal for a day that we hope will never come but that given enough time almost certainly will. And the result of that rehearsal was clear. We can push back. Not perfectly, not yet against every threat, but enough to know that the effort is worth continuing. Enough to know that with more data, more missions, more investment, and more time, we can build a shield that our descendants will rely on long after we are gone. Think of the generations that will come after us. Our grandchildren, their grandchildren, the countless human beings who will walk this planet in the centuries and millennia ahead. If we are wise enough to protect them, they will inherit whatever we build. If we build a comprehensive planetary defense system, one that detects every threatening asteroid, deflects the ones on collision courses, and maintains the readiness to respond to emergencies, then those future generations will live under a safer sky than any that came before. Not a perfectly safe sky. The universe will always be dangerous, but a sky that is watched, tracked, and defended. If we do not build that system, if we allow the attention to fade, the funding to lapse, the institutional momentum to dissipate, then our descendants will be no better off than the dinosaurs. They will know the threat exists. They will have read about Dart in history books. They will understand that their ancestors had the knowledge and the technology to protect them, and they will wonder why we did not. The night sky looks the same tonight as it did before Dart. The same stars, the same moon, the same slow sweep of the Milky Way across the darkness. But something has changed, something invisible and profound. Between those stars, among that ancient light, a small rock is orbiting on a slightly different path. A path changed by us. A path changed by intention, by mathematics, by engineering, by the quiet determination of a species that looked up at the sky and decided not to be afraid of it. We are, in the end, a species that tells stories. And the story of Dart is one of the most important we have ever told. It is the story of a species that was born under a dangerous sky and, after billions of years of evolution and thousands of years of civilization, finally learned to push the danger away. Not all of it, not yet, but enough to matter, enough to prove that the effort is real and the physics is on our side. Dimorphos still orbits Didymos, the solar system still turns, the asteroids still drift on their ancient paths, and on a small blue planet orbiting an ordinary star, a species that has existed for 300,000 years, a species made of stardust and mathematics and stubborn hope, continues to watch the sky. The dinosaurs could not do that. No species before us could do that. And if we are wise, no species after us will ever have to learn to do it alone. The rock moved, we moved it, and the universe noticed nothing, but we did.